When we look into the night sky with the naked eye, the stars appear like tiny points of light, scattered like glitter across a vast black canvas. To most people, they all seem similar, just small specks far away, twinkling quietly with no hint of their true nature. But the reality could not be more different. Some of these stars are unimaginably larger than our own sun, so immense that if you could place them side by side, the sun would shrink to a grain of sand compared to a mountain. To understand these giants among the stars, we must first ask a deceptively simple question. What does it mean for a star to be big? There are several ways to measure the size of a star, and each tells a different story. The most obvious measure is radius, the distance from the center of the star to its surface. In this sense, stars like Betelgeuse and Antares are titans, swelling outward to diameters hundreds or even more than 1,000 times that of the sun. Imagine the sun as a glowing orange, its light bathing the planets. Now imagine a star that would fill the orbit of Jupiter, so swollen that Earth would lie deep inside its fiery outer layers. This is what we mean by radius. But size can also be defined by mass, the total amount of matter that makes up a star. A star like R13601, buried inside the Tarantula Nebula, is not the largest in radius, but holds hundreds of times the mass of the Sun. That means its gravity crushes inward with an intensity far beyond what we can imagine, forcing it to burn through its nuclear fuel at a staggering rate. These massive stars shine with light, millions of times brighter than the Sun, flooding their surroundings with energy. In this measure of size, mass is a kind of hidden power, one not always reflected in sheer physical radius. Then there is luminosity, the total energy radiated by the star each second. Some stars outshine the Sun by factors of hundreds of thousands or even millions, pumping radiation into space so fierce that it reshapes nearby gas and dust. This definition of bigness highlights the destructive and creative influence a star can have on its cosmic neighborhood. The Sun, which seems so dominant to us, is actually an ordinary middleweight star. It is about 1.4 million kilometers across, with a surface temperature of about 5,800 degrees Celsius, and a luminosity that defines the standard by which astronomers measure other stars. But compared to the true giants, our Sun is modest. Betelgeuse, the red supergiant in the constellation Orion, swells to more than 700 times the radius of the Sun. If you placed Betelgeuse at the center of our solar system, its surface would stretch beyond the orbit of Mars. Earth would be consumed within its vast outer layers. Antares, the red heart of Scorpius, is of similar scale, another swollen giant star whose fiery atmosphere dwarfs our own solar system's inner worlds. And then there is VY Canis Majoris, once considered the largest known star by radius. Estimates once placed it at nearly 1,400 times the radius of the Sun. To grasp that, imagine placing the star at the center of the solar system. Its surface would extend past the orbit of Jupiter. Earth, Mars, and even the asteroid belt would vanish inside its outer atmosphere. The difference in scale is almost incomprehensible. If Earth were the size of a grain of pepper, the Sun would be like a small marble. But a star like VY Canis Majoris would be more like a sphere larger than a house, looming so vast that the mind struggles to hold the image. Visualizing these scales is essential. Picture standing on Earth and looking at the Sun in the sky. It appears about the size of a coin held at arm's length. Now imagine Betelgeuse or UY Scuti, the record holder for largest known radius. If one of those giants were placed in the same position as the Sun, their surface would cover half the sky, blazing with such intensity that Earth would be incinerated instantly. The sense of smallness, of fragility, becomes overwhelming. Yet these immense stars are not serene or stable. Their vast size comes at a cost. The balance that holds a star together is delicate, a tug of war between gravity pulling inward and the heat of nuclear fusion pushing outward. For stars as large as these, that balance is precarious. They swell and contract, belching out enormous clouds of gas their surfaces boiling with convective currents larger than our entire planet. Their light flickers and changes because the star itself is unstable, straining to hold itself together against its own bulk. And so, we begin to see the truth. The biggest stars are not only large, they are unstable monsters, struggling against their own gravity and burning themselves out at terrifying speeds. These giants live brief lives, only a few million years compared to the billions that our sun enjoys. Their size is both their majesty and their doom. The journey into their world has only just begun, but already the scale should unsettle us. What we have seen so far are only the first steps, comparisons that reveal how small our solar system really is. But the deeper we look, the more terrifying the giants become. They are not just larger than the sun. They are forces of nature on a scale that bends the imagination, and their fates are as violent as their lives are immense. Their enormous bulk comes with consequences that ripple through the cosmos. A star like Betelgeuse does not remain fixed in size, but swells and contracts over time, its surface shifting as though the entire star is breathing. The outer layers of such a giant are not tightly bound by gravity, so great waves of gas are constantly being pushed outward into surrounding space. Sometimes the star ejects entire arcs of material, creating vast shells of glowing hydrogen and dust. These eruptions are not gentle puffs of smoke, but colossal storms, more massive than entire planets, moving outward at thousands of kilometers per hour. If Earth were caught inside such a storm, our planet would be torn apart in an instant. These giants appear red because their swollen surfaces are relatively cool compared to smaller stars like the Sun. The surface temperature of Betelgeuse is only about 3,500 degrees Celsius, far cooler than the 5,800 degrees Celsius of the Sun. Antares is similar, with a surface temperature closer to 3,400 degrees Celsius. But appearances are deceptive. Even though their surfaces are cooler, their sheer size means their luminosity is staggering. Betelgeuse shines with the power of more than 100,000 suns, and Antares radiates a similar energy. What they lack in heat, they more than make up for in volume, so the total light streaming outward overwhelms everything nearby. VY Canis Majoris is even more extreme. At nearly 1,400 times the radius of the Sun, its volume is incomprehensible. It could hold billions of suns inside its bloated envelope. Yet such size is unstable. Observations show that VY Canis Majoris is losing mass at a furious rate, casting off material that forms huge clouds of dust around it. When astronomers look at this star, they do not see a crisp disk of light. Instead, they see a turbulent, chaotic structure surrounded by arcs and knots of gas, evidence that the star is tearing itself apart. Its light varies unpredictably as vast convective currents churn within its outer layers, each cell of rising and falling gas larger than the orbit of Earth. Even more astonishing is the comparison with UY Scuti, the current record holder for largest radius. Located about 9,500 light-years away in the constellation Scutum, UY Scuti expands to nearly 1,700 times the radius of the Sun. If placed in the center of the solar system, its surface would extend beyond the orbit of Jupiter, consuming Mercury, Venus, Earth, Mars, and the asteroid belt along the way. To describe this in simple terms, imagine the entire orbit of Jupiter glowing as the surface of a star. Every planet we know would be inside it. Such scale is hard for the human mind to picture, because our everyday sense of size collapses in the face of these magnitudes. The instability of these hypergiants comes from the delicate balance inside them. A star burns by fusing hydrogen into helium in its core. This process releases energy, which pushes outward, counteracting the crushing weight of gravity. In a normal star like the Sun, this balance can hold for billions of years. But in a giant star, the mass pressing inward is so great that the fusion rate must be correspondingly faster to resist collapse. The result is a furious blaze that consumes fuel at an astonishing pace. Betelgeuse, Antares, and Uy-Scuti have lifespans of only a few million years, mere flickers compared to the long life of the Sun. In cosmic terms, they live fast and die young. The evidence of their instability can be seen in the variations of their brightness. Betelgeuse, for example, dimmed dramatically in late 2019, leading many to wonder if it was about to explode in a supernova. In reality, astronomers discovered that a massive ejection of gas had formed a dust cloud that temporarily obscured its light. Even at such vast distances, these events are visible to us, reminding us of the volatile and unpredictable lives of these titans. For Earth, the comparison is sobering. Our entire world is just one small planet, orbiting an average star. The Sun, though central to our existence, is ordinary. Yet when we look at stars like Betelgeuse or Uy-Scuti, we are confronted with objects so immense that they dwarf our entire solar system. Imagine Earth as a single cell in a human body, fragile and insignificant, while these giants are entire beings towering over us. Their scale defies comprehension, their lifespans are brief, and their deaths are violent. The lesson is clear. Size is not just a matter of radius or mass, it is also about instability and impermanence. The giants among the stars reveal the limits of stability in the universe. They show us that there is a threshold beyond which stars cannot remain calm, where their very existence is a struggle against their own enormity. And this is where the story begins to shift, because these giants, for all their magnificence, are doomed. Their vast size, their unstable nature, and their furious rate of fuel consumption mean that they cannot endure. Already, they are nearing the ends of their lives, and their deaths will be as spectacular and horrifying as their lives are majestic. The universe is filled with these unstable monsters, each one a ticking clock counting down to destruction. What lies ahead for these stars is not peace, but violence, not stability, but collapse. Their final moments will shake the cosmos, releasing energy on a scale that can sterilize entire regions of space. To understand the horrifying power of the biggest stars, we must follow them into the heart of their destruction. We must watch them unravel, collapse, and explode. Only then will we grasp the true magnitude of the giants among the stars. The giants that loom in the darkness are not merely astronomical curiosities. They are warnings written across the heavens. Each swollen red supergiant or luminous hypergiant represents a limit reached, a boundary crossed in the physics of stars. If a star is too small, gravity never compresses its core enough to ignite nuclear fusion, and it becomes a cold, failed star, a brown dwarf. If a star is of medium size, like the Sun, it burns for billions of years in relative stability, keeping its planets warm and alive. But when a star grows truly massive, its existence becomes a precarious dance. Its gravity tries to crush it inward, and its fusion burns ever more furiously to push outward. There is no lasting peace in such a balance. The bigger the star, the shorter and more violent its life must be. Take Betelgeuse again, a familiar red beacon in Orion's shoulder. It is so large that if you could carve it into hollow shells the size of the Sun, it would take more than 1 billion of those suns to fill it. And yet its life is already nearing its end. Astronomers estimate that Betelgeuse may only have a few 100,000 years left before it explodes as a supernova. That sounds long to us, but it is an eye blink in cosmic time. The Sun will still be shining billions of years from now, long after Betelgeuse has gone. Imagine watching 2 candles burning, one steady and enduring, the other flaring so brightly that it burns itself out almost at once. This is the fate of the giants. Antares tells the same story. Its red light dominates the constellation of Scorpius, but its interior is unstable, roiling with convection currents that transport energy from its core to its vast surface. Each rising plume of gas is larger than the orbit of Earth, a continent of plasma boiling through the star's atmosphere. Its glow is not steady, but restless, flickering as the star swells and contracts. To To stand on a planet near Antares, if such a place could exist, would be to live under a sky filled by a single, monstrous red star stretching across your horizon. That world would be bathed in searing radiation and storms of stellar wind so fierce that no life as we know it could endure. And then comes VY Canis Majoris, cloaked in veils of dust and gas that it has expelled in its own desperate struggle to maintain balance. Astronomers have traced arcs of material reaching out billions of kilometers from the star, remnants of eruptions in which it hurled away pieces of itself. This is not a stable giant, but a wounded colossus, tearing apart under the strain of its own bulk. Its life is a slow disintegration, a prelude to the final catastrophe. Yet, even VY Canis Majoris is outdone in sheer radius by UY Scuti. It swells to such enormity that describing it becomes an exercise in futility. Imagine the orbit of Jupiter glowing like a living surface. Imagine every inner planet swallowed, every trace of Earth incinerated long before you reach the star's edge. Its radius is so great that light itself takes more than 2 hours to travel from one side of the star to the other. That is not the diameter of a galaxy, not the span of a solar system, but a single star. What does this mean for us? It means that our sun, which seems so enormous and powerful to us, is in truth a small thing in the cosmic hierarchy. Earth clings to its light and warmth as though it were the center of everything, yet our star is only average, a common yellow dwarf among hundreds of billions. Against the backdrop of Betelgeuse, Antares, VY Canis Majoris, or UY Scuti, our sun is an ember. But the lesson of the giants is not only about scale, it is about impermanence. The bigger a star becomes, the more it must fight to remain stable, and the faster it burns its fuel. The giants live in a state of tension that cannot last. They may be the most awe-inspiring sights in the universe, but they are also doomed from the moment of their birth. Their instability is a harbinger of the violence to come. We stand on Earth and look up, and the stars seem peaceful, yet the truth is far from tranquil. The greatest among them are monsters of instability, their surfaces boiling, their light flickering, their outer layers streaming away into the void. They are like great cosmic volcanoes, swelling toward eruption, their power building toward a final, devastating release. This is the threshold where awe turns to terror. To understand these stars is to realize that the universe is not only beautiful, but also profoundly violent. The very same forces that forge worlds and elements also destroy them. The giants among the stars embody this duality. They are both creators and destroyers, both majestic and horrifying. As we move forward, we will focus on one of these titans in detail, VY Canis Majoris. Once thought to be the largest star in existence, it offers a perfect case study of what it means to be a stellar giant. It is a colossal being, casting off its layers into space, fighting for balance, and inching toward an inevitable fate. Through VY Canis Majoris, we will see more clearly what it means for a star to reach such size, and we will begin to understand the unimaginable consequences when such a monster finally dies. There is a point in the night sky where the constellation of Canis Major stretches across the heavens, and hidden within its boundaries lies a star so immense that for a time it held the crown as the largest known star. This star is VY Canis Majoris, a red hypergiant located about 3,900 light-years from Earth. That distance alone is staggering. A light-year is nearly 10 trillion kilometers, the distance that light, moving at almost 300,000 kilometers per second, travels in a single year. And yet, even from so far away, VY Canis Majoris has made itself known through the sheer immensity of its presence. Once thought to be the largest star in existence, it was estimated to swell to a radius of more than 1,400 times that of the Sun. To grasp this, imagine placing the star at the center of our solar system. Its surface would extend far beyond the orbit of Jupiter. The entire region where the planets Mercury, Venus, Earth, Mars, and the asteroid belt lie would be engulfed deep within its fiery envelope. The gas giants themselves would find their orbits brushing against its outer atmosphere. It is almost impossible to visualize such enormity without resorting to metaphor. If Earth were a grain of pepper and the Sun a small marble, VY Canis Majoris would be a sphere larger than a house, dominating everything around it. But the true story of this star is not only its size, it is a tale of instability, of a colossus that cannot hold itself together. Observations of VY Canis Majoris show that it is shedding its outer layers into space, casting off massive clouds of gas and dust. These ejections are not minor events but eruptions of material more massive than entire planets. Over time, the star has surrounded itself with a complex nebula of arcs and knots of matter, drifting outward into the interstellar medium. Each arc is a signature of violence, a reminder that the star is slowly tearing itself apart. When astronomers peer at VY Canis Majoris through powerful telescopes, they do not see a simple round sphere. Instead, they see chaos. Its outer layers are distorted, irregular, filled with convective plumes so vast that each one is larger than the orbit of Earth. Imagine oceans of plasma boiling upward in waves bigger than planets, crashing down with the energy of worlds colliding. The star's surface is not a serene glow, but a storm that never ceases, a struggle between gravity's crushing pull and the desperate outward push of radiation. VY Canis Majoris is also dimmed by its own self-destruction. The clouds of dust it expels scatter its light, making it fainter to our eyes than it would otherwise appear. What we see from Earth is only a fraction of its true brightness, obscured by the veil of material it has thrown into space. But this shroud is not permanent. Over thousands of years, the dust will drift outward, enriching the surrounding galaxy with elements forged in the star's core. These are the raw materials for new stars, new planets, and perhaps even new life. Yet this process comes at a terrible cost. The star is burning through its fuel at an astonishing pace, and it cannot last. Hypergiants like VY Canis Majoris live only a few million years, a brief spark in cosmic time. Already, this star has passed through much of its hydrogen and helium, fusing heavier elements in its core. Each step in this progression brings it closer to collapse, closer to the moment when it will no longer be able to resist the inward crush of gravity. When that moment comes, the result will be catastrophic. We know from astrophysics that such a star cannot simply fade away. Its death will be violent. It may explode as a supernova or even as a hypernova, a detonation so powerful that it outshines entire galaxies for a brief moment. Alternatively, it may collapse directly into a black hole, its entire mass vanishing behind an event horizon, leaving nothing but darkness where once there was light. Either way, the end of VY Canis Majoris will send shockwaves across space, scattering elements and energy on a scale that defies comprehension. Already we can see the warning signs. The mass loss, the instability, the chaotic surface all point to a star approaching its final act. In cosmic terms, that act could occur at any time. It might be tens of thousands of years from now, or it might already have happened, with the light of the explosion still traveling toward us across the gulf of space. From Earth, we would see the heavens ignite as a new beacon blazes into existence, outshining every other star in the sky. For weeks, perhaps months, it would be visible in daylight, a reminder that even the mightiest stars must eventually fall. VY Canis Majoris is therefore not only a marvel, but a portent. It is a symbol of what happens when stars push the boundaries of size and power. They cannot endure. They burn too furiously. They swell too vastly, and they cast themselves into instability. The Colossus in Canis Major is already unraveling, already on the path to destruction. And when it finally goes, the universe will tremble with the force of its death. But even VY Canis Majoris is not the end of the story. For all its immensity, For all its instability, astronomers have discovered that there are stars even larger. Stars that swell beyond even this colossal radius, pushing the limits of what a star can be. To find them, we must look deeper into the galaxy, into constellations like Scutum, where UY Scuti holds the record as the largest known star by radius. If VY Canis Majoris is a wounded colossus, UY Scuti is the record breaker, a giant so vast that its surface would engulf Jupiter and everything within its orbit. And so our journey continues, from the colossal to the record-breaking, from VY Canis Majoris to UY Scuti, each one revealing a deeper truth about the terrifying power of the biggest stars in the universe. The immensity of VY Canis Majoris becomes even more unsettling when we compare it to our own existence. Earth, with its thin atmosphere and fragile ecosystems, orbits a stable star that has burned for nearly 5 billion years and will continue for billions more. Yet VY Canis Majoris, in its furious brilliance, has lived only a few million years and is already dying. Its life is like a colossal bonfire that burns so fiercely it consumes itself almost as soon as it begins. What does this mean for us, who are sheltered by the calm light of the sun? It means that in the universe, stability is a rare gift, and we happen to live under a star that offers it. If Earth had been born near a hypergiant like VY Canis Majoris, there would never have been time for life to form. The star would have collapsed and exploded long before evolution could unfold. Astronomers who study VY Canis Majoris often describe its behavior as chaotic, unpredictable, even violent. The dust arcs and knots around it are evidence of repeated eruptions in which the star has hurled away parts of itself into space. Some of these arcs extend thousands of astronomical units outward, a scale so vast it defies human imagination. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Now picture thousands of those units filled with glowing clouds of gas and dust. This is the reach of the star's self-destruction. It is not a gentle shedding of material, but a continual violence that reshapes the space around it. The material expelled by VY Canis Majoris is not wasted. The universe is a recycler. The hydrogen, helium, carbon, and heavier elements cast off into the void will someday become part of new stars and planets. Perhaps far in the future, long after the star itself has vanished, atoms from its body will form into new worlds where life might emerge. But that future lies beyond the horizon of our time. For now, what we see is a dying colossus, still burning, still unstable, still fighting to maintain its balance. The study of VY Canis Majoris has also revealed how little we truly understand about the largest stars. Its size has been revised many times as astronomers have improved their methods. Early measurements suggested a radius of nearly 1,500 times that of the Sun, but later refinements placed it closer to 1,000 times, still immense beyond comprehension. These variations are not due to mistakes, but to the difficulty of measuring such an unstable, irregular star shrouded in dust. It is a reminder that the cosmos resists easy definitions. Even when we focus on one of the largest known stars, our instruments strain to capture its reality. For those who seek to understand stellar evolution, VY Canis Majoris is a laboratory of extremes. Its mass loss rate is tens of millions of times greater than the Sun's. Its luminosity exceeds hundreds of thousands of suns. Its convective cells are so large that they could swallow planets whole. Each observation challenges our models, pushing us to refine our understanding of what stars can be. The star is a living paradox. It is both bright and fading, powerful and disintegrating, immense and fragile. And yet, for all its majesty, its fate is sealed. The day will come when VY Canis Majoris exhausts the fuel in its core. Gravity will take control, pulling inward with irresistible force. The outer layers may collapse and rebound in a titanic explosion, casting off material into space with such violence that it briefly outshines an entire galaxy. Or perhaps the collapse will be so complete that the star will vanish almost without a trace, its matter crushed into a black hole from which not even light can escape. The choice between these fates depends on its final mass and internal structure, details still uncertain, but the end will be catastrophic in either case. The thought that such an explosion could already have occurred is sobering. If VY Canis Majoris has collapsed, the light of that event is still racing across space toward us, a silent messenger that has traveled for nearly 4,000 years. When it arrives, it will blaze in our skies with a brilliance that will rival the moon. Night will turn to day, and humanity will witness firsthand the death of a star so vast it once seemed beyond comprehension. It is difficult to overstate how profound such an event would be. For astronomers, it would be a chance to observe processes that shape galaxies, to see the birth of heavy elements that will someday form planets and life. For humanity at large, it would be a humbling reminder of our smallness, a demonstration that the universe is alive with forces far beyond our control. And for those who look at the sky with awe, it would be an encounter with the raw power of creation and destruction. But as staggering as VY Canis Majoris is, it no longer holds the record for the largest star by radius. That title belongs to UY Scuti, a hypergiant in the constellation Scutum, whose swollen envelope makes VY Canis Majoris seem modest by comparison. If VY Canis Majoris is a colossal giant on the verge of death, UY Scuti is the record breaker, the one that stretches the very definition of what a star can be. To understand the full scope of stellar gigantism, we must now turn our gaze toward this even more extraordinary monster, whose size would engulf not only Earth and Mars, but even Jupiter itself. VY Canis Majoris lingers in the night sky as a reminder of the extremes that nature can reach. Even from thousands of light years away, it has captivated astronomers because it forces us to confront the boundaries of stellar physics. Its swollen radius, its turbulent surface, and its relentless mass loss all mark it as a star nearing the end of its journey. But beyond the facts and numbers, there is a deeper truth. To look upon VY Canis Majoris is to witness fragility disguised as power. It shines with the brilliance of hundreds of thousands of suns, yet it is collapsing beneath the weight of its own grandeur. This duality is what makes VY Canis Majoris so compelling. Its enormous size is not a sign of health or longevity, but of instability. Imagine a bonfire that flares brightly for moments before it dies, compared to a candle that burns gently for hours. VY Canis Majoris is that bonfire, overwhelming in its momentary brilliance, but destined for a swift and violent end. The very physics that allow it to grow so large also guarantee its downfall. Its fusion furnace cannot endure the strain, and so the star lashes out, shedding its body into the cosmos piece by piece. When we study its convective surface, we see a kind of stellar weather that makes any storm on Earth seem insignificant. Gigantic plumes of plasma rise and fall, each dwarfing our planet many times over. Imagine a hurricane so large that Earth itself would vanish inside its eye, and imagine dozens of such hurricanes raging across the star's face at once. That is the scale of violence occurring constantly on VY Canis Majoris. Its light flickers as these convective cells churn, and its dust clouds veil it, making the star seem to breathe in and out as it struggles against its fate. The materials it casts into space tell another part of the story. These elements are not just drifting debris, they are the seeds of the future. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were forged in stars that lived and died long before the sun existed. When VY Canis Majoris finally erupts or collapses, it will scatter new layers of heavy elements into the galaxy, enriching the interstellar medium for generations of stars yet to come. In this sense, its destruction will be a gift, a contribution to the cycle of cosmic creation. Its death will be violent, but it will not be meaningless. Still, there is something unsettling about such grandeur. We are used to thinking of stars as eternal, unchanging points of light. Yet here we see that even the most magnificent among them is fragile. In cosmic terms, VY Canis Majoris has only moments left. It may be tens of thousands of years, but on the scale of the universe, that is the blink of an eye. At any moment, its life could end, and a cataclysmic detonation could send out a beacon that reaches our skies. Humanity might someday awaken to find the heavens transformed, a new star blazing where before there was only darkness. The fascination with VY Canis Majoris lies not just in its size, but in what it represents. It is the embodiment of impermanence. It shows us that nothing, not even the largest star in the sky, can last forever. Its immense radius, its unstable surface, and its shroud of dust are all signs that it is in its final chapters. And though it may seem distant, the processes unfolding within it are part of the same story that gave rise to us. The iron in our blood was forged in the collapse of stars like this. In a very real sense, we are connected to its fate. Yet for all its magnitude, VY Canis Majoris is only one among many giants. Once considered the largest, its crown has since passed to others. This does not diminish its importance, but rather emphasizes the diversity of extremes among the stars. Each hypergiant reveals another aspect of the universe's ability to push physics to the edge. Where VY Canis Majoris shows us instability and mass loss, other giants reveal even greater radii, or greater mass, or more intense luminosity. Together, they paint a picture of a universe that is both extravagant and unforgiving. The next step in our journey takes us from VY Canis Majoris to UY Scuti, a star that redefines the notion of size. If VY Canis Majoris seems vast beyond comprehension, UY Scuti stretches even further, swelling to a radius nearly 1,700 times that of the Sun. To imagine it is to stretch the human mind to its limits, for its surface would reach beyond Jupiter's orbit, swallowing nearly all the familiar worlds of our solar system. It is the record breaker, the benchmark against which all other giants are measured. And like VY Canis Majoris, it is not merely a giant, but a doomed one, fragile in its enormity and teetering on the brink of collapse. And so, the path continues. VY Canis Majoris has shown us what it means for a star to tear itself apart, but UY Scuti will show us how far the universe can stretch the very definition of a star. From the colossal to the record-breaking, from instability to fragility, we now move deeper into the story of giants, each step bringing us closer to the horrifying power of the largest stars in existence. There is a star in the constellation Scutum that redefines our sense of scale. It is called UY Scuti, and among all the stars we have measured, it holds the record for the largest radius. Located nearly 9,500 light-years away, UY Scuti is a red hypergiant whose size challenges the limits of our imagination. Where VY Canis Majoris once claimed the crown, UY Scuti now stands as the ultimate example of how vast and fragile a star can become. To grasp the enormity of UY Scuti, imagine the Sun once more at the center of the solar system. Its light and warmth reach out to Pluto and beyond, but its physical surface is small compared to the cosmic giants. Now replace the Sun with UY Scuti. Its surface would not stop at Mercury or Venus or Earth. It would stretch past Mars, past the asteroid belt, past Jupiter. The star's surface would engulf everything within that orbit. Earth, our fragile home, would lie deep within its blazing atmosphere, destroyed long before we could ever hope to comprehend the sight. The radius of UY Scuti is estimated to be nearly 1,700 times that of the Sun. To put this in perspective, if the Sun were the size of a small coin, UY Scuti would be the size of a small building. Light itself, moving at 300,000 kilometers per second, would take more than 2 hours to travel from one side of the star to the other. We are accustomed to thinking of stars as points of light, but in this case, a single star spans a distance larger than the entire orbit of Jupiter. This immensity does not come without a price. Like other hypergiants, Uy Scuti is unstable. Its outer layers are tenuous, barely bound by gravity, and prone to being cast into space in violent eruptions. Observations show that the star's brightness fluctuates, sometimes dimming and brightening as it pulsates. These variations are signs of internal turbulence, as the star struggles to balance the outward pressure of fusion against the inward pull of gravity. Each pulse is a reminder that the star is not serene but fragile, poised on the edge of collapse. The luminosity of Uy Scuti is staggering. It radiates nearly 500,000 times more energy than the Sun. Every second, it pours out enough light to equal the output of hundreds of thousands of suns. And yet, because of its great distance and the dust that surrounds it, Uy Scuti is invisible to the naked eye. This is one of the paradoxes of the cosmos. The largest known star, blazing with near incomprehensible power, is hidden from human sight. Its light dimmed by the very material it has cast into space. Only with the aid of telescopes can we bring it into view. Astronomers studying Uy Scuti see in it a portrait of a dying star. Like Vy Canis Majoris, it has only a few million years of life in total, and most of that is already behind it. It has consumed much of its hydrogen and is fusing heavier elements in its core. The more massive a star becomes, the faster it burns its fuel, and Uy Scuti is no exception. Its enormous size is a symptom of its instability, a sign that it is entering the final stages of its life. The destiny of Uy Scuti is sealed. It will not quietly fade away. At the end of its brief existence, it will either explode in a supernova or collapse directly into a black hole. If it explodes, the detonation will be unimaginably powerful, releasing more energy in seconds than the Sun will radiate in its entire lifetime. The shock waves will carve new structures in the interstellar medium, and the elements forged in its core will be cast into space, becoming the seeds for new generations of stars and planets. If it collapses directly into a black hole, it will vanish almost instantly, leaving behind only darkness and gravity. Uy Scuti's scale invites comparisons, but every comparison fails to capture the reality. We can say it would engulf Jupiter. We can say light takes 2 hours to cross it. We can say its volume is billions of times greater than the Sun, but these are numbers that overwhelm rather than clarify. To truly imagine Uy Scuti is to let go of human sense of proportion and accept that it exists on a scale beyond us. It is not a star as we commonly understand one. It is a phenomenon, a swollen colossus, a fleeting burst of cosmic extravagance. And like all extravagances, it cannot last. The very size that makes Uy Scuti remarkable is the same size that guarantees its demise. The balance of forces within it is unstable. Gravity pulls inward, fusion pushes outward, and the two are locked in a war that can only end one way. The star will lose. Gravity always wins in the end. Uy Scuti stands as both a record and a warning. It shows us the maximum of what a star can be before it unravels. It tells us that beyond a certain point, greatness becomes fragility, and immensity becomes doom. To study it is to confront the limits of stellar evolution and to glimpse the violence waiting at the end of a giant's life. But as we leave Uy Scuti, the story does not end with size alone. There are stars that may not stretch as far in radius, but whose mass dwarfs even the largest hypergiants. In the tarantula nebula of the Large Magellanic Cloud lies a star called R136A1, more massive than 250 suns combined. If Uy Scuti is the record breaker for size, R136A1 is the record breaker for weight, a star so massive that it radiates millions of times more light than the Sun. And it is to this colossal furnace of mass and radiation that our journey now turns. The story of Uy Scuti is not only about its immensity, but about the strange tension that exists in stars at the limits of size. When astronomers measure its pulsations, they see a star struggling to maintain balance. Its surface swells and contracts over months, a slow breathing that hints at chaos within. Each contraction pushes matter outward, each expansion weakens its grip on the outer layers, and the result is a cycle of instability that can hurl vast clouds of gas into space. What we observe as subtle changes in brightness are in fact the convulsions of a dying giant, its interior shifting as it prepares for the end. This instability is amplified by the tenuous nature of its outer layers. In a star as large as UY Scuti, gravity weakens dramatically at the surface. The mass of the star is spread across such an enormous radius that its grip on its atmosphere is fragile. The result is a bloated star whose outer shell is little more than a veil, easily disturbed by currents from within. Imagine the atmosphere of Earth suddenly expanding until it stretched beyond the orbit of the Moon. It would no longer be tightly bound, and the slightest disturbance could sweep it away. This is the condition of UY Scuti's outer envelope, vast, swollen, and unstable. The sheer size of the star makes it almost impossible to represent accurately. If Earth were placed near the surface of UY Scuti, our planet would not orbit the star as it does the Sun. Instead, it would lie inside the star's seething atmosphere, vaporized in an instant. Even Jupiter, with its immense bulk, would orbit within the star's glowing layers. Saturn would circle close to its fiery edge. Only Uranus and Neptune might remain beyond its visible surface, though they too would be bathed in its intense radiation. It is a solar system engulfed, a vision of destruction that shows us how fragile our worlds truly are. The luminosity of UY Scuti is another marker of its extraordinary power. At nearly 500,000 times the output of the Sun, the star radiates more energy in a second than our Sun produces in days. This radiation is not evenly distributed. The dust and gas surrounding UY Scuti scatter and absorb much of its light, hiding its true brilliance from our view. To the naked eye, it is invisible, cloaked by the very material it has expelled. Yet behind that veil, the energy release is staggering, a beacon that floods its local region of the galaxy with light and heat. In many ways, UY Scuti is a paradox. It is the largest star we have ever measured in radius, yet it is also one of the most fragile. Its enormity is not a sign of strength, but of weakness. It is like a balloon filled to the point of bursting, its outer layers stretched thin and unstable. The larger it becomes, the closer it comes to collapse. Unlike the Sun, which maintains stability for billions of years, UY Scuti has only a fleeting existence measured in millions. Its size is both its glory and its doom. The fate of such a star is grim but spectacular. As its core exhausts lighter elements and begins to fuse heavier ones, the balance between gravity and radiation becomes ever more precarious. The fusion of carbon, neon, oxygen, and silicon proceeds in ever shorter stages, each lasting thousands or even mere hundreds of years. When iron begins to accumulate in the core, the end will arrive quickly. Iron cannot be fused to release energy, so the star will no longer have the pressure it needs to resist gravity. The core will collapse in a fraction of a second, and the star will unleash a supernova, or perhaps a hypernova, a cataclysm that will ripple across the galaxy. When that moment arrives, UY Scuti will vanish as a star and leave behind either a neutron star or a black hole, depending on how much of its mass remains after the explosion. If it collapses into a neutron star, the result will be an object only a few kilometers wide, but so dense that a teaspoon of its matter would weigh billions of tons. If it becomes a black hole, it will disappear behind an event horizon, leaving only the warping of space and the pull of gravity as evidence of its existence. In either case, its immense presence will give way to something compact and terrifying. It is unsettling to realize that UY Scuti's life is already nearing its end. In cosmic terms, its final act is imminent. Whether it explodes tomorrow or in 100,000 years, the difference is negligible when compared to the age of the universe. We may be living in the last quiet moments before one of the most massive stellar deaths our galaxy will ever witness. And yet, as vast and record-breaking as UY Scuti is, it is not the most massive star. Radius is one way of measuring greatness, but mass tells another story. There are stars smaller in radius, but so heavy that their gravity bends the rules of physics. In the Tarantula Nebula of the Large Magellanic Cloud, we find R136A1, a star with more than 250 times the mass of the Sun. If UY Scuti is the swollen record breaker of size, R136A1 is the heavyweight champion of mass, and its story takes us deeper into the terrifying power of the universe's giants. The true immensity of UY Scuti becomes most vivid when we try to imagine it alongside the familiar. Picture the Sun as a glowing sphere on a football field. In comparison, Earth would be a tiny seed only a few millimeters wide, circling at a modest distance. Now replace the Sun with UY Scuti. The field would no longer be large enough to contain its bulk. You would need to step back not a few meters, but kilometers, and still you would struggle to see its edge. Earth would not orbit around it. It would be swallowed whole, lost deep within its glowing, turbulent layers. Light, the fastest thing in the universe, takes just over 8 minutes to reach us from the Sun. Across UY Scuti, that same light would require more than 2 hours to travel from one side to the other. The scale is so enormous that human metaphors collapse under its weight. A single star, one among hundreds of billions in our galaxy, spans a distance greater than the orbits of nearly every planet we know. This is what it means to call UY Scuti the record breaker. And yet, its majesty is fragile. Observations reveal that UY Scuti is surrounded by shells of gas and dust, evidence of violent mass loss. The star is actively unraveling, its outer layers cast outward into interstellar space. This is not a slow drift, but a torrent, a steady bleeding of material that reshapes its environment. Each shell carries the story of an eruption, a moment when the star could no longer contain itself. These shells will someday blend into the galaxy, contributing to the raw material for new stars and planets. In this way, even as UY Scuti dies, it is already preparing for future generations of cosmic creation. The irony of UY Scuti is that its greatness is inseparable from its doom. Stars become hypergiants only when they are nearing the end of their lives. They bloat outward as their cores contract and their fusion changes, swelling into monstrous forms that cannot last. Their lifespans are short compared to the billions of years enjoyed by smaller stars. For UY Scuti, existence is a rapid, furious blaze. It will live only a few million years in total, and then it will vanish forever. For Earth, this raises unsettling questions. If a star, like UY Scuti, were located within a few dozen light years of us, its final explosion could have devastating consequences. The blast of radiation and high-energy particles could sterilize planets, stripping away atmospheres and scorching surfaces. Fortunately, UY Scuti lies far enough away that its death will not threaten our world. But the thought remains. The universe is filled with such giants, and some of them are closer than we might wish. Astronomers see in UY Scuti not only a record breaker, but a key to understanding the fate of massive stars. By studying its pulsations, its eruptions, and its luminosity, they refine models of how hypergiants live and die. Each observation adds to our picture of stellar evolution, teaching us how the largest stars enrich galaxies with heavy elements and how they collapse into exotic remnants. UY Scuti is both a marvel and a warning, a reminder that the universe's beauty is inseparable from its violence. And so, as we leave the swollen form of UY Scuti, we must turn our attention to another extreme. If UY Scuti is the largest star in radius, there exists another that outmatches it in sheer mass. In the Tarantula Nebula of the Large Magellanic Cloud, nearly 160,000 light-years away, burns R136A1. With more than 250 times the mass of the Sun, it is a furnace of unimaginable intensity, radiating millions of times more light than our star. Where UY Scuti overwhelms by size, R136A1 overwhelms by weight and energy. Together, they reveal that the giants of the universe can be monstrous in different ways, and their power is always a harbinger of violent ends. The journey now shifts from the swollen fragility of UY Scuti to the crushing density of mass in R136A1, where radiation sculpts entire nebulae and the boundaries of what a star can be are stretched to their very limit. Far beyond the familiar constellations of our night sky lies a region of astonishing violence and beauty. In the neighboring Large Magellanic Cloud, a satellite galaxy to our own Milky Way, sprawls a vast stellar nursery known as the Tarantula Nebula. Within this turbulent sea of gas and dust, new stars are born in great numbers, some small, some large, and a very few so colossal that they seem to challenge the very laws of physics. Among these, one star stands above the rest. It is called R136A1, and it is the most massive star ever discovered. While UY Scuti may hold the record for sheer radius, R136A1 is unmatched in mass. It is more than 250 times heavier than the Sun, a weight so great that the star defies the conventional limits of stability. For decades, astronomers believed that stars could not exceed about 150 solar masses, for anything larger would collapse under its own gravity or blow itself apart with its own radiation. Yet here, shining within the heart of the Tarantula Nebula, is a star that mocks those limits. R136. A1 exists in a category of its own, a furnace so immense that it bends our theories to their breaking point. The luminosity of R136A1 is staggering. It blazes with the power of nearly 9 million suns, flooding its surroundings with ultraviolet radiation so intense that it sculpts the entire nebula around it. Great pillars of gas, carved into fantastical shapes, are eroded by the relentless blast of photons pouring outward from this single star. Where the light strikes, molecules are torn apart. Where the wind collides with gas, shock fronts form, igniting regions of new star birth. R136A1 is not simply a star, but a cosmic engine, reshaping its environment through sheer radiative force. If you could place R136A1 at the center of our solar system, its radius would not reach as far as UY Scuti's. In fact, it would likely extend only a few dozen times beyond the Sun's radius, making it physically smaller in size than the swollen hypergiants. But size is not the same as mass, and here lies the difference. The density of R136A1's core, the weight of its substance, the ferocity of its radiation, all exceed anything the swollen giants could achieve. This is the distinction between bulk and weight, between a balloon inflated to monstrous proportions and a compact furnace that blazes with unmatched intensity. R136A1 burns with such fury because of its mass. The greater the mass of a star, the greater the gravitational pressure at its core. That pressure forces nuclei together at extraordinary rates, driving fusion at levels far beyond ordinary stars. In our Sun, hydrogen fuses into helium at a steady pace, producing enough energy to last billions of years. In R136A1, hydrogen is fused at a rate so ferocious that the star will exhaust its fuel in just a few million years. It is the classic tale of the massive star. The brighter the flame, the shorter the life. Its radiation is not only a destructive force, but also a creative one. The shockwaves and winds it generates trigger new bursts of star formation within the Tarantula Nebula. The very existence of R136A1 reshapes the destiny of its environment. Without such giants, galaxies would not evolve as they do. They stir the interstellar medium, enriching it with heavier elements, dispersing energy, and creating the conditions for new worlds to form. Yet this creative role is inseparable from the violence they unleash. To live near such a star would be impossible. Any planet orbiting within a reasonable distance would be stripped of its atmosphere in moments, bathed in ultraviolet radiation that sterilizes all surfaces. It is a sobering thought that nature allows such extremes. On Earth, life thrives under the steady glow of a stable star. But elsewhere, in regions like the Tarantula Nebula, stars like R136A1 rage with such intensity that they burn away any chance of life close to them. They are not stars for nurturing, they are stars for forging and destroying, great furnaces whose purpose seems to be reshaping galaxies on scales far beyond our comprehension. But even as R136A1 astonishes us with its power, it carries within it the same doom as every giant. Its immense mass guarantees that its life will be brief and its death catastrophic. No star of such weight can end quietly. It is destined either for a hypernova, an explosion of almost unimaginable power, or for direct collapse into a black hole, vanishing in an instant into eternal darkness. The question is not if, but when. For a star as massive as R136A1, the countdown to collapse is already ticking. It has lived perhaps 1 or 2 million years, a brief flicker compared to the sun's billions, and in only a few million years more, it will be gone. The Tarantula Nebula will be shaken by its death, and its remnants will carry the heavy elements that will someday form new stars, new planets, perhaps even new life. Its legacy will be written in the chemistry of the cosmos, even as its presence vanishes into either fire or silence. R136A1 is thus both a marvel and a menace. It demonstrates that the universe can create stars more massive than we once thought possible. It shows us the extremes of radiation and fusion, the heights of power that matter can achieve under gravity's relentless hand. And yet, it also shows us the limits of stability, the inevitability of collapse, and the fragility that hides behind even the greatest strength. From Betelgeuse and Antares to VY Canis Majoris and UY Scuti, we have seen giants of radius, swollen colossi, whose size overwhelms our imagination. But with R136A1, we face something different. A giant of mass, a titan whose weight bends the rules, and whose radiation reshapes the very structure of a nebula. The next steps in our journey will follow this theme further, examining not only how these giants live, but how they die. For if their lives are brief, their deaths are spectacular beyond measure, and it is in those deaths that we see the full horrifying power of the largest stars in the universe. The brilliance of R136A1 is not the brilliance of calm endurance, but of desperation. It blazes because its immense weight crushes its core into such extremes that fusion cannot help but proceed at an extraordinary pace. Each second it consumes matter equivalent to the mass of Earth in order to sustain its radiation. The Sun, by comparison, consumes only a fraction of that mass over much longer spans of time. This is why R136A1 shines with millions of times more light than the Sun, but also why its lifespan will be so short. Its existence is a fever, a storm of fire that burns itself to exhaustion. When we look at the Tarantula Nebula through telescopes, we see not only the light of this star, but its impact. The nebula itself is shaped by its presence. Towers of gas rise like colossal sculptures, carved into strange patterns by ultraviolet light. Shockwaves ripple through the interstellar medium, compressing gas clouds and triggering new generations of starbirth. R136A1 is not merely a part of this nursery, it is the dominant force within it, the architect of its forms. It is a reminder that stars are not isolated entities. They shape their surroundings, and the most massive among them reshape entire regions of space. The radiation of R136A1 is so intense that it ionizes hydrogen across vast distances. Atoms are stripped of their electrons, leaving behind glowing plasma that illuminates the nebula. This glow is not passive, but alive, flickering with the energy poured out by the star. Where the winds collide with denser clumps of gas, knots of matter compress, igniting new stars in their turn. In this way, The life of R136A1 feeds the birth of others, a paradox of destruction and creation. It sterilizes its immediate environment while seeding the conditions for future worlds. If there were a planet orbiting close to R136A1, it would be unrecognizable as a place where life could exist. The ultraviolet flux would shred its atmosphere in moments. The stellar winds would blast its surface with particles traveling at thousands of kilometers per second. The planet itself might be torn apart by the sheer intensity of radiation pressure. This is not a star that can nurture life. It is a star that obliterates, and yet it is also a star that ensures that somewhere else, far away, the seeds of new life may eventually be sown. The physics of such a star strain against the limits of what is possible. Radiation pressure should in theory prevent a star from becoming as massive as R136A1. The outward force of light, scattering off particles in the star's outer layers, should blow material away before it can accumulate. And yet, nature found a way. Perhaps through rapid accretion in its earliest youth, perhaps through collisions of massive protostars in the dense cluster of the Tarantula Nebula, this star gathered more than 250 suns worth of mass. The fact of its existence forces astronomers to refine their theories of star formation. It stands as evidence that the universe can stretch the rules further than we once believed. Its surface temperature is tens of thousands of degrees Celsius, far hotter than that of the Sun or of the red hypergiants. This heat means that its light is predominantly in the ultraviolet, invisible to human eyes but devastating to molecules. Its color, if we could see it, would be a dazzling blue-white, the hue of searing intensity. Such hot stars burn quickly, their lives compressed into a fraction of the time available to smaller, cooler stars. R136A1 is a beacon of fleeting power, destined to vanish soon after it was born. To imagine its death is to imagine one of the most violent events in the cosmos. If it ends as a hypernova, the explosion will release 10 times more energy than an ordinary supernova. A hypernova can outshine an entire galaxy, flooding space with gamma rays that sweep across light years. Such an event would sterilize worlds unlucky enough to lie within its path. It is possible that R136A1 could one day unleash such a cataclysm, though at its great distance from Earth we would be safe. Still, the thought that such destructive potential exists within a single star is humbling. The alternative is that R136A1 might collapse directly into a black hole, bypassing even the spectacle of an explosion. In that case, its immense mass would vanish behind an event horizon, leaving no light behind, only the pull of gravity. The transformation from the most luminous star to the darkest object in the universe would be instantaneous. One moment a blazing beacon of millions of suns, the next a silent void. That is the fate awaiting this giant, either in fire or in darkness. It is strange to consider that we live in an age where such a star exists. Given its short lifespan, the odds of seeing one during humanity's time in the cosmos are small. Yet here it is, blazing in the Tarantula Nebula, offering us a chance to study the extreme edge of stellar physics. In its light, we read the story of the universe's creativity and violence, its ability to build wonders that cannot last. And as awe-inspiring as R136A1 is, it also leads us to a deeper question. What is the value of size and mass if both guarantee collapse? The giants of the cosmos seem destined to die young, their power always their undoing. To answer this, we must look not only at their lives but at their deaths. For in their destruction, they release energies that shape galaxies, they scatter elements that build planets, and they ignite phenomena more terrifying than anything we have yet encountered. The next stage of our journey will follow the lives of such giants to their inevitable ends, tracing the path from furious burning to catastrophic collapse. It is there, in the moment of death, that their true power is revealed. The life of R136A1 is a story written in extremes. From the moment of its birth in the dense cluster of the Tarantula Nebula, it was destined to be extraordinary. While most stars form with masses similar to the Sun or smaller, this one accumulated hundreds of times that amount, pulling in matter from its surroundings with insatiable hunger. Some astronomers even suspect that collisions between smaller protostars may have contributed to its growth, merging their masses into a single colossal body. However it formed, the result is something that bends the boundaries of possibility, a star so massive that its very existence is a puzzle. The cluster in which R136A1 resides contains many other hot, massive stars, but none approach its sheer weight. Together, they flood the nebula with light, but this one stands above them all, its radiation so intense that it dictates the shape and evolution of the region. Imagine an orchestra of blazing stars, each contributing to the cosmic symphony, but with one conductor whose power dominates every note. Without R136A1, the Tarantula Nebula would be very different. With it, the nebula becomes a theatre of extremes, sculpted by ultraviolet fire. Such a star does not simply shine, it consumes. Its gravity squeezes its core to unimaginable pressures, forcing hydrogen nuclei to fuse at a pace far beyond the Sun's. The result is a torrent of energy, a flood of photons that pushes outward with irresistible force. This outward push, radiation pressure, is so great that it nearly counteracts the weight of gravity pulling inward. The balance between the two forces is delicate, and in stars of this size, it becomes precarious. The star hovers at the edge of stability, constantly at risk of tearing itself apart. Already, R136A1 has shed a portion of its mass through powerful stellar winds. Streams of particles blow outward at thousands of kilometers per second, carrying away material equal to many suns over the course of its life. These winds contribute to the nebula's glow, fueling shockwaves that compress gas clouds and trigger further star formation. But they also erode the star itself, a steady attrition that reminds us even the greatest colossus is not eternal. In giving energy and material to its surroundings, the star shortens its own life. To observers on Earth, R136A1 is faint despite its brilliance, for distance diminishes even the brightest light. It takes nearly 160,000 years for its radiation to reach us, crossing the gulf between galaxies to arrive as a point of light in our telescopes. By the time we see it, the star has already lived and changed. The image before us is history, a glimpse into a moment long past. It may already be different than we perceive, perhaps even gone, collapsed into darkness, though we will not know until its final light reaches us. The death of R136A1 will be one of the most spectacular events the cosmos can provide. If it explodes as a hypernova, it will release energies so vast that even from the Large Magellanic Cloud, the light would be visible to the naked eye on Earth. For weeks, the night sky would be transformed, dominated by the blaze of a star tearing itself apart. Gamma rays would pour forth in beams, scouring the galaxy around it, though we would be too far to be harmed. It would be both a sight of beauty and a reminder of destruction, a cosmic firework that dwarfs any power humanity could ever wield. If instead it collapses directly into a black hole, the event may pass almost silently from our perspective. One moment, a star blazing with the light of millions of suns, the next, gone. No explosion, only an absence, a region of space where gravity reigns so absolute that nothing escapes. Such a transformation is in its own way even more terrifying. To imagine the most luminous star becoming the darkest object in the universe is to confront the extremes of creation and annihilation. Whatever its fate, R136A1 will leave behind a legacy. The heavy elements it forges in its core will be cast outward if it explodes, seeding the interstellar medium with oxygen, carbon, and iron. These will become part of new stars, planets, and perhaps even life. If it collapses into a black hole, it will become a gravitational anchor, a seed that may one day merge with others to form something larger, perhaps even contributing to the birth of a supermassive black hole in a galactic center. Either way, the life and death of this one star will echo across millions of years, shaping the future in ways we cannot predict. From the swollen bulk of UY Scuti to the crushing mass of R136A1, we see that the giants of the universe express their power in different forms. One overwhelms by sheer radius, the other by weight and radiation. Both are unstable, both are doomed, and both reveal the same truth. In the cosmos, greatness comes with fragility. The larger the star, the more violent its life, the shorter its span, and the more catastrophic its end. Our journey now turns to these endings, to the fiery deaths that await such titans. For their lives are only the prologue. It is in their deaths, in the unimaginable detonations of supernovae and hypernovae, that they reveal their full and horrifying power. And so we move from life to death, from the blazing brilliance of giants to the cataclysms that follow, where the true scale of stellar violence is laid bare. Every star is born with a fate written in its mass. From the moment gravity pulls gas and dust together into a glowing sphere, the weight of that sphere determines how long it will live, how it will shine, and how it will die. A small star, with only a fraction of the sun's mass, will smolder gently for tens of billions of years, its light steady and quiet. A star like our sun, a middleweight among the cosmos, will burn hydrogen in its core for about 10 billion years, before swelling into a red giant and finally fading into a white dwarf. But the giants, the truly massive stars, are bound to a different story. Their lives are measured not in billions of years, but in millions, brief sparks compared to the vastness of time, and their deaths are among the most violent events the universe can produce. The process begins deep within the heart of the star. Nuclear fusion is the engine that powers every star, the transformation of lighter elements into heavier ones under the crushing force of gravity. In our sun, hydrogen fuses into helium at a pace that balances the inward pull of gravity with the outward push of energy. This balance is delicate but stable, and it allows the sun to shine steadily for billions of years. In a giant star, however, the balance is precarious. The greater mass of the star means the pressure at its core is far higher, and fusion proceeds at a rate millions of times faster than in the sun. The effect of this furious burning is twofold. First, it produces a luminosity far greater than that of smaller stars. A giant star may shine hundreds of thousands or even millions of times brighter than the sun, flooding its surroundings with energy. Second, it shortens the star's life dramatically. What the sun achieves in billions of years, a hypergiant burns through in only a few million. The brighter the flame, the shorter the life. This is the tragic irony of the giants. Their grandeur is fleeting, their brilliance doomed to fade almost as soon as it begins. As the giant consumes its hydrogen, it moves on to heavier fuels. The helium that builds up in its core begins to fuse into carbon and oxygen, releasing still more energy. In time, the carbon fuses into neon, the neon into oxygen, and the oxygen into silicon. Each stage proceeds more rapidly than the one before. Where hydrogen burning may last millions of years, silicon burning may last only days. The closer the star comes to producing iron in its core, the closer it comes to its death. Iron is the limit. Unlike lighter elements, iron cannot release energy by fusing into heavier nuclei. When iron begins to accumulate, the core of the star becomes a trap. The fusion that once pushed outward against gravity stops providing pressure. Gravity, relentless and unopposed, takes over. The core collapses in a fraction of a second, and the life of the star comes to an end. But for a giant, death is never quiet. The collapse of the core triggers a rebound that sends shockwaves rippling outward through the star's layers. In an instant, the outer shell is blasted into space in a titanic explosion. The energy released in this moment can equal the total output of the sun over its entire 10 billion year lifespan. To any observer, the star becomes millions of times brighter than before, briefly outshining an entire galaxy. This is a supernova, the death cry of a giant, a detonation so immense that it reshapes the galaxy around it. Yet even here, there are levels of power. Some of the most massive stars, those that dwarf even Betelgeuse or Antares, may unleash explosions far beyond the scale of an ordinary supernova. These are hypernovae, cataclysms 100 times more energetic, accompanied by jets of gamma radiation that tear through space like cosmic lances. Such an event marks not only the end of a star, but the sterilization of everything unlucky enough to be caught in its path. The life of a giant star is therefore a paradox. It is short but brilliant, unstable but powerful, destructive but creative. In its core, the elements of life are forged, yet its death can extinguish life across entire regions of space. It is both a creator and a destroyer, both a beacon and a threat. And as we trace the steps of these lives and deaths, we are reminded that our own existence is tied to this cycle. Without the death of giants, there would be no carbon in our bodies, no oxygen in our lungs, no iron in our blood. We are, in the most literal sense, the children of dying stars. This chapter is the bridge between life and death, between the blazing brilliance of giants like R136A1 and the terrifying explosions that end them. To understand the horrifying power of the biggest stars, we must linger here in the space between, where nuclear fire shapes destiny and where collapse waits like a shadow beneath the glow. The story of a giant star's life is one of constant change, as though the star itself is racing against time. Unlike the sun, which rests in long phases of stability, the giant lurches from one stage of burning to the next, each phase shorter than the last. It is a countdown written in fire. The core contracts, heats, and ignites new fuels, while the outer layers expand and contract in response, creating a restless cycle of instability. The entire star becomes a dynamic, turbulent system, never still, always on the brink of transformation. The speed of these changes is astonishing. A star like Betelgeuse may burn hydrogen in its core for only a few million years, a brief lifetime compared to the Sun's 10 billion. Once the hydrogen is exhausted, helium fusion lasts a fraction of that time, perhaps hundreds of thousands of years. The subsequent stages burn faster still. Carbon may last 1,000 years, neon just a single year, oxygen only months, and silicon mere days. It is as if the star is sprinting toward a finish line, each step faster and more desperate than the last, until the inevitable collapse. During these frantic stages, the outer layers of the star are in turmoil. Convection currents churn enormous plumes of plasma, carrying energy from the core to the surface. These plumes are not small ripples, but titanic structures larger than Earth's orbit, rising and falling like oceans of fire. The surface flickers and shifts, swelling and contracting as the interior struggles to maintain balance. The result is a star that seems to breathe, its light varying in brightness as it fights to hold itself together. The winds from such a star are fierce. Stellar winds strip away material at rates thousands of times greater than the sun's, carrying matter into space at speeds of thousands of kilometers per second. Over its short life, a giant may lose more than half its mass in this way, surrounding itself with clouds of gas and dust that glow in the light of the star. These outflows are both a symptom of instability and a preparation for death, for when the final explosion comes, it will hurl this material outward to become part of the galaxy's fabric. Even as it teeters toward collapse, the giant continues to create. Each new stage of fusion produces heavier elements, building the periodic table step by step inside its core. Carbon, oxygen, neon, magnesium, silicon, and finally iron, all forged in the furnace of a star that knows it is running out of time. Without this cycle, the universe would be barren of the elements needed for life. The air we breathe, the bones that support us, the tools we craft, all exist because ancient giants once burned and died, scattering their ashes across the cosmos. The inevitability of collapse looms over this process. As iron builds up in the core, It cannot release energy through fusion. The balance that has held the star together for millions of years begins to fail. Gravity, always waiting, always patient, seizes control. In less than a second, the core implodes, shrinking from thousands of kilometers across to just a few dozen. The density becomes so extreme that protons and electrons are crushed into neutrons, releasing a flood of neutrinos that stream outward in a burst of energy. This is the trigger, the moment when the collapse turns into an explosion. The shockwave born in that instant rips through the star's outer layers, tearing it apart with unimaginable force. What was once a stable giant becomes a blazing beacon of destruction. The explosion is so bright it can be seen across galaxies, outshining billions of ordinary stars. For days or weeks, it dominates the sky, a reminder of both the glory and the fragility of stellar life. This is the death of a giant, violent beyond comprehension, yet essential to the cycle of creation. For nearby worlds, the consequences are catastrophic. A supernova within a few dozen light years of Earth could strip away the atmosphere, irradiate the surface, and sterilize life. Fortunately, none of the nearby red supergiants are close enough to pose an immediate threat. But elsewhere in the galaxy and across the universe, such deaths are common. At any moment, countless stars are collapsing and exploding, reshaping their neighborhoods with blasts of energy. To witness the life of a giant star is to see the universe at its most extravagant. It is a brief, furious existence, filled with instability and ending in violence. And yet, from that violence comes the material of new worlds, the elements of life, and the seeds of future creation. Giants live fast and die young, but their deaths ensure that the cosmos continues to evolve. The final act of their lives, the moment of collapse and explosion, is so spectacular that it deserves its own focus. For it is not only light and matter that emerge from these cataclysms, but forces so powerful that they can shape galaxies and threaten life across light years. To move closer to the horrifying power of the biggest stars, we must step into the heart of their death throes, where fusion fails, collapse takes over, and the universe trembles with their final roar. The end of a giant's life is not only a spectacle, but also a transformation. In the violence of collapse and explosion, the very identity of the star changes, and what is left behind is something fundamentally new. When the core of the star implodes, it compresses matter into states that defy ordinary experience. At the moment of collapse, gravity overwhelms all other forces, and the building blocks of atoms are forced together. What remains depends on the mass of the collapsing core, and the result can be as strange as it is terrifying. If the collapsing core is small enough, perhaps a few times the mass of the Sun, the result is a neutron star. This object, only a dozen kilometers across, is unimaginably dense. A teaspoon of neutron star matter would weigh billions of tons on Earth. Its surface gravity is so intense that if you stood on it, you would be crushed instantly. Neutron stars are often left spinning, and their rapid rotation, combined with intense magnetic fields, produces beams of radiation that sweep through space. When these beams cross our line of sight, we see pulses of light, and so we call these remnants pulsars. They are the corpses of giants, still emitting signals across the void. But if the core is more massive still, gravity does not stop at neutrons. It continues to collapse until nothing can resist it, not even light. The result is a black hole, a region of space where gravity is absolute and escape is impossible. A black hole may begin as the remnant of a giant star, but over time it can grow by consuming surrounding matter, becoming a monster that reshapes entire galaxies. In this way, the death of a single giant can sow the seeds of the darkest objects in the universe. The material thrown outward during the explosion has its own destiny. It rushes into space at thousands of kilometers per second, colliding with surrounding gas and dust, heating it until it glows. For centuries, even millennia, the expanding shell of a supernova remains visible as a nebula, a glowing memorial to the star that once was. These remnants are not just beautiful. They are chemical factories dispersing the elements forged in the star's core. Calcium, oxygen, silicon, and iron are scattered across interstellar space, ready to become part of new planets, oceans, and living beings. The cycle is clear. Giants live short and violent lives, but in their deaths, they enrich the universe. Without them, the cosmos would be barren, filled only with hydrogen and helium. There would be no carbon for life, no oxygen for breath, no iron for blood. Every atom heavier than helium in our bodies was once created in the furnace of a star and cast into space by its death. To say we are made of stardust is not poetry, but fact. We are the children of giants who lived and died long before the sun was born. The brevity of their lives is part of their meaning. A giant like R136A1 may last only a few million years, but its impact will echo across billions. Its death will trigger the formation of new stars, scatter elements for new worlds, and perhaps create a black hole that endures until the end of time itself. The universe wastes nothing. Even the most violent destruction is also creation, feeding the endless cycle of birth and death that defines the cosmos. And yet, for all this grandeur, there is something profoundly unsettling about the lives and deaths of these giants. They remind us that permanence is an illusion, that even the most massive and powerful objects in the universe are fragile. Their deaths are warnings written in light, messages that nothing, no matter how great, can last forever. In their final moments, they blaze with such intensity that they outshine galaxies. But even this brilliance is only temporary, fading into darkness, or into a remnant that bears little resemblance to the star that once was. This is the life and death of a giant, a brief, furious blaze of brilliance, ending in collapse and explosion, scattering the seeds of future stars and worlds. It is a cycle that has played out countless times across the galaxy and will continue for billions of years to come. It is a cycle that gave rise to us and will someday give rise to others. To understand it is to see both the fragility and the power of the universe, to recognize that even destruction is part of creation. But the story does not end here. For some of the largest giants, their deaths unleash not only supernovae, but something even more violent. When the collapse of a star produces explosions 100 times more powerful, the universe trembles with forces so extreme that they outshine entire galaxies and send gamma rays racing across space. These are hypernovae, explosions beyond imagination, and they are the next chapter in our journey into the horrifying power of the biggest stars. The death of a giant star is among the most violent events in the universe, but for the most massive of these giants, death is even more extreme. When a star with dozens or even hundreds of solar masses collapses, the explosion that follows is not a mere supernova. It is something far more powerful, an event we call a hypernova. These cataclysms release energy on a scale that defies comprehension, detonations so violent they can briefly outshine entire galaxies and send destructive radiation sweeping across space. If a supernova is the thunder of a collapsing star, then a hypernova is the roar of the cosmos itself. The distinction between a supernova and a hypernova lies in scale. A typical supernova may release 10 to the power of 44 joules of energy, more than the sun will emit in 10 billion years. A hypernova, however, can release 10 times as much, rivaling the combined brilliance of billions of stars. For days or weeks, a single hypernova can dominate the light of a galaxy, its brilliance visible across the depths of the universe. And behind that light lies violence almost beyond imagination. The process begins as it does for any giant. The core of the star, exhausted of fuel, collapses under its own weight. But in the case of the largest stars, the collapse is even more catastrophic. The core implodes with such force that it may immediately form a black hole. Matter from the surrounding layers falls inward, spiraling into the newborn singularity. As it does, it releases colossal amounts of energy, channeled not only outward in a spherical explosion, but also along narrow beams of radiation that pierce the cosmos. These are the signatures of hypernovae, the moments when the death of a star shakes the universe on a galactic scale. The debris from the explosion is hurled outward at speeds approaching a tenth of the speed of light. Entire planets, if they existed nearby, would be obliterated in an instant, their matter scattered into space. Dust and gas clouds are swept aside, reshaped by the expanding blast. The surrounding interstellar medium is seeded with heavy elements, enriching the galaxy with the raw materials of life. Hypernovae, destructive as they are, play a crucial role in shaping the chemistry of the universe. Without them, there would be no gold, no uranium, no heavy elements beyond iron. They are the cosmic forges where the rarest atoms are created. But their violence is not confined to matter alone. Hypernovae are often accompanied by bursts of gamma radiation, the most energetic form of light. These gamma-ray bursts are among the most dangerous phenomena in the universe. They are focused into narrow beams that can travel across galaxies, stripping atmospheres from planets and sterilizing entire star systems. To be within range of such a burst is to face extinction, as no shielding can withstand the flood of high-energy photons. Fortunately, the chances of one striking Earth are low, but the possibility remains, a reminder that the universe is not always a safe place for life. Astronomers believe that some hypernovae may occur when massive stars collapse into rapidly spinning black holes. The rotation funnels matter into jets, focusing the energy into narrow beams that blast outward at near light speed. These jets, aligned by chance with our line of sight, appear to us as sudden flashes of gamma radiation, lasting only seconds, but releasing more energy than the sun will emit in its entire lifetime. To witness one is to glimpse the raw power of stellar collapse, concentrated into a moment of almost unimaginable intensity. Hypernovae are rare compared to supernovae, but they are not uncommon on cosmic timescales. Somewhere in the universe, perhaps right now, a giant star is collapsing into darkness, unleashing a hypernova that will echo for millions of years. Its light may already be on its way to us, traveling across the gulf of space, a silent signal of destruction that will one day brighten our skies. When it arrives, it will be a reminder that the cosmos is alive with forces far beyond our control. Yet for all their terror, hypernovae are also essential. They are the engines of chemical enrichment, the events that scatter the heaviest elements into galaxies. Without them, the periodic table would be incomplete, and life as we know it would be impossible. They are both destroyers and creators, annihilating worlds while preparing the raw material for new ones. The universe thrives on this paradox, weaving destruction and creation into a single cycle that repeats endlessly. As we step further into the study of hypernovae, we see the full extent of what the giants of the cosmos can unleash. Their deaths are not merely endings, but transformations, reshaping galaxies and seeding the universe with the ingredients of life. But within these explosions lies something even more terrifying. For in the narrow beams of gamma radiation that hypernovae produce, the destructive power of the cosmos becomes focused into weapons of extinction. To understand these bursts is to confront the true horror of the giants' deaths, the moments when stars reach beyond their own systems and threaten life across galaxies. The power of a hypernova is almost impossible to grasp, and yet scientists have pieced together its mechanics through the remnants scattered across the galaxy. When astronomers observe supernova remnants, they see expanding shells of glowing gas spreading out through space, lit by the energy of the explosion. Hypernova remnants, by contrast, reveal even greater violence. Their shockwaves are faster, their energy signatures brighter, and their chemical fingerprints richer in the heaviest elements. These are the traces of events that dwarf even the most powerful ordinary supernovae. In the core of a collapsing hypergiant, conditions reach extremes beyond imagination. As the core collapses into a black hole, the infalling material forms an accretion disk, spinning at a significant fraction of light speed. Friction and magnetic fields within this disk funnel energy into jets that blast outward through the star's poles. These jets punch through the collapsing layers, focusing the explosion into narrow beams of unimaginable intensity. The result is not a simple spherical detonation, but a cosmic lance, a directed outpouring of radiation and matter that can travel across billions of light years. The energy involved in such jets is staggering. In a few short seconds, they release as much energy as the sun will emit over its entire 10 billion year lifetime. To a distant observer, this energy appears as a gamma-ray burst, a sudden flash that can briefly outshine the rest of the universe. If the jets happen to be aligned with Earth, they arrive without warning, carrying enough power to sterilize entire biospheres. For worlds unlucky enough to be caught in the path of such a burst, survival is impossible. The very molecules of life are torn apart by the flood of high-energy photons. This terrifying potential is balanced by rarity. Hypernovae are not everyday events. They occur only in the deaths of the most massive stars, those at least 30 or 40 times the mass of the Sun, and even then only when conditions align to produce focused jets. Still, in a universe filled with hundreds of billions of galaxies, even rare events happen often somewhere. Every few seconds, somewhere in the cosmos, a gamma-ray burst flashes into existence, the visible sign of a hypernova ripping a star apart. Most are far away, so distant that their effects cannot reach us, but their light travels across space to be recorded by our telescopes. Each one is a warning, a reminder that the universe is filled with weapons of extinction. Yet even in their violence, hypernovae are creative. The shock waves they generate compress surrounding clouds of gas, triggering new waves of star formation. The heavy elements they scatter, gold, platinum, uranium, become the seeds of planets and the building blocks of civilizations. Without hypernovae, there would be no rare metals for technology, no radioactive elements to drive the heat of Earth's interior, no diversity of matter beyond the lighter elements. It is a strange thought that the same explosions that could wipe out life also enable its existence in the first place. The scale of destruction caused by a hypernova cannot be overstated. If such an event occurred within a few thousand light-years of Earth, its radiation could damage the ozone layer, stripping away protection from solar ultraviolet rays. If it occurred within a few hundred light-years, the gamma-ray burst itself could directly sterilize the surface of our world. Fortunately, no stars capable of producing such a threat are close enough to us now. Betelgeuse, for example, will explode someday, but its orientation and distance mean it poses no danger to Earth. Still, the possibility remains elsewhere in the galaxy, and in distant epochs of Earth's past, some scientists suggest gamma-ray bursts may have played a role in mass extinctions. For astronomers, studying hypernovae and their associated bursts is not only a matter of understanding destruction, but also of unlocking the secrets of extreme physics. The processes occurring in the accretion disk around a newborn black hole, the dynamics of relativistic jets, the creation of heavy elements, all are mysteries revealed in part by these violent deaths. Observing a hypernova is like opening a window into the most extreme laboratory the universe can provide, a place where matter and energy behave in ways that cannot be reproduced on Earth. It is also a reminder of perspective. From our vantage point on Earth, life seems permanent, stars seem eternal, and the night sky appears calm. But beyond that illusion lies a universe alive with violence. Every second, hypernovae are detonating, gamma-ray bursts are flashing, and galaxies are being reshaped by the deaths of giants. We see only a fraction of this activity, yet it defines the evolution of the cosmos. Hypernovae are not the final step in the story of stellar death. They are dramatic, violent, and terrifying, but the true horror lies in the beams of gamma radiation they unleash. These bursts carry the destructive potential of hypernovae across galaxies, transforming a single star's death into a threat for worlds light years away. To understand the full reach of stellar destruction, we must now turn to these bursts themselves, the cosmic killers that embody the universe's most concentrated violence. The detonation of a hypernova is not the end of the story, but the beginning of its legacy. The expanding shell of debris continues to move outward for thousands of years, sweeping through the interstellar medium like a storm front. As it collides with surrounding gas and dust, it ignites them in glowing filaments, creating supernova remnants that span dozens of light years. These remnants are not just scars of destruction, they are the seeds of creation. Within them, dense clumps form where gravity gathers material, setting the stage for new stars to emerge. The death of one giant gives birth to countless smaller suns, continuing the cycle of stellar life. The heavy elements forged in the hypernova's core and hurled outward in its explosion enrich the galaxy with new possibilities. Gold, platinum, uranium, and other heavy atoms that do not form in ordinary fusion processes appear in these blasts. Every ring, every circuit, every trace of rare metal mined from Earth owes its existence to such cosmic violence. It is a sobering truth that the jewelry on a hand or the fuel in a reactor was born in the death throes of a hypergiant star, scattered across space in an explosion that dwarfs anything humanity could ever create. For astronomers, hypernovae are also milestones of time and distance. Their brilliance makes them visible across billions of light years, serving as beacons that illuminate the history of the universe. By studying their light, scientists can probe the early cosmos, measuring how galaxies formed and evolved. These explosions are not only acts of violence, but tools of knowledge, revealing truths about the universe that could not otherwise be seen. Hypernovae have helped chart the expansion of space itself, anchoring our understanding of cosmology in the light of dying giants. Yet the violence cannot be ignored. The gamma-ray bursts that accompany some hypernovae remain the most concentrated form of destruction known. For a planet unlucky enough to lie within the path of a beam, there is no defense. Even across thousands of light years, the radiation can sterilize surfaces and strip atmospheres, erasing life in moments. These bursts are reminders that the universe is not built for comfort. It is vast, violent, and indifferent, and life persists only in the sheltered corners where such forces cannot reach. Still, hypernovae are necessary. Without their destructive power, the universe would lack the diversity of matter required for planets and life. Without their bursts of energy, galaxies would evolve differently, star formation proceeding in other ways. They are the violent architects of the cosmos, shaping both the dangers and the opportunities for life to arise. We owe our existence to them, even as we fear what they represent. The paradox of the hypernova is clear. It is both the most terrifying and the most essential event in the universe. It can sterilize entire systems, yet it creates the elements that make life possible. It can outshine galaxies, yet it leaves behind remnants that nurture new stars. It is destruction and creation woven together, inseparable, each giving meaning to the other. And so, as we leave behind the hypernova, we carry forward its lessons. The giants of the universe do not die quietly. Their deaths ripple outward, reshaping galaxies, scattering elements, and sending bursts of radiation that can reach across light years. To understand the full horror of their power, we must now look directly at the gamma-ray bursts themselves, those narrow beams of annihilation that transform a single star's death into a threat for distant worlds. These are the true cosmic killers, the sharp edge of the universe's violence, and they are the next chapter in the tale of the horrifying power of the biggest stars. When a giant star dies in a hypernova, its destruction does not end with light and matter alone. In some cases, the collapse unleashes beams of radiation so concentrated and so powerful that they sweep across galaxies like invisible scythes. These are gamma-ray bursts, the most energetic explosions known in the universe. If hypernovae are the thunderclaps of dying stars, then gamma-ray bursts are their lightning bolts, narrow, focused, and capable of devastation on a scale far beyond their source. A gamma-ray burst is born when the core of a massive star collapses into a black hole. The matter spiraling into the newborn singularity forms a disk, and from the poles of that disk erupt jets of plasma accelerated to nearly the speed of light. Within those jets, particles collide and radiate, releasing energy in the form of gamma rays, the most energetic form of light. Unlike the spherical glow of a supernova, these bursts are concentrated into narrow beams, each only a few degrees across. To a distant observer, the burst appears as a sudden flash of light, lasting seconds or minutes, yet in that brief time, outshining all the stars in the observable universe combined. The numbers defy comprehension. In just 10 seconds, a gamma-ray burst can release as much energy as the sun will emit in 10 billion years. The light of entire galaxies cannot rival the brilliance of these beams. If one were to occur within a few thousand light years of Earth, aligned with our planet, the results would be catastrophic. The burst would strip away the ozone layer, exposing the surface to deadly ultraviolet radiation from the sun. The atmosphere itself could be ionized, leading to chemical changes that poison the air. Life on Earth, from the smallest microbes to the largest animals, would be at risk of extinction. And yet, we know gamma-ray bursts are real. Telescopes in orbit detect them regularly, flashing across the sky without warning. They occur a few times each day somewhere in the universe, the death cries of stars so far away that their light has traveled billions of years to reach us. Most are harmless, occurring at distances where their beams cannot touch our world. But their frequency is a reminder of how common such violence is. The calm sky above us hides a universe alive with destruction. There is evidence that gamma-ray bursts may have shaped the history of life on Earth itself. Some scientists propose that one of the mass extinctions in Earth's past, perhaps the Ordovician extinction more than 400 million years ago, could have been triggered by a nearby burst. The sudden loss of atmospheric ozone, followed by a surge in ultraviolet radiation, could have devastated ecosystems worldwide. Whether or not this theory is true, it is a chilling reminder that life on Earth depends not only on local stability, but also on the absence of cosmic catastrophes. Gamma-ray bursts come in two varieties. Long bursts, lasting tens of seconds or more, are linked to the collapse of massive stars in hypernovae. Short bursts, lasting less than 2 seconds, are thought to arise from collisions between neutron stars or between a neutron star and a black hole. Both types release unimaginable energies, and both demonstrate the universe's ability to focus destruction into moments so brief and yet so powerful that they echo across billions of light years. The danger of a gamma-ray burst lies in its focus. Unlike the broad glow of a supernova, which radiates in all directions, a burst is a weapon of precision. Only those worlds unlucky enough to lie in the path of its beam are affected. But for those worlds, the effect is total. A planet can be sterilized in moments, its atmosphere stripped, its biosphere erased. For civilizations elsewhere in the galaxy, the death of a star could mean the death of their world, not by explosion or collision, but by a flash of invisible light from light years away. To study gamma-ray bursts is to confront the most concentrated violence in the universe. They remind us that the cosmos is not gentle, that the forces shaping galaxies and stars are indifferent to life. And yet, like hypernovae, they play a role in the grand cycle of creation. The jets and shocks they produce scatter heavy elements, fueling the formation of new worlds. The destruction they cause is matched by the opportunities they create, a paradox that runs through all of cosmic evolution. But the horror remains. To look up at the night sky and know that at any moment, somewhere across the universe, a gamma-ray burst is flashing into existence is to feel both awe and fear. It is a reminder that life clings to its fragile hold in a universe dominated by forces of annihilation. And as we continue our journey into the power of the biggest stars, we will see that the legacy of these giants does not end even with their bursts of radiation. Their final act is to collapse into the darkest of all objects, black holes, where even light itself cannot escape. Gamma-ray bursts are not just powerful, they are precise. Their beams of radiation are focused into narrow cones, meaning that most of the universe never sees them. But when those cones happen to align with a distant observer, the effect is overwhelming. Telescopes on Earth and in orbit record them as sudden flashes, lasting anywhere from a fraction of a second to several minutes, often followed by an afterglow that lingers in X-ray, ultraviolet, visible, and radio wavelengths. These afterglows allow astronomers to trace the origins of the bursts, locating them in galaxies billions of light-years away. The distance of most bursts is a comfort. Even the most powerful of them, if they occur far enough across the cosmos, pose no threat to Earth. But the sheer intensity of these explosions means that distance is the only protection. A burst occurring within our own galaxy, aimed directly at us, would be catastrophic. The gamma rays would strip away the upper layers of the atmosphere, destroying the ozone shield and allowing lethal solar radiation to pour through. The chemistry of the air itself would be altered, filling it with nitrogen oxides that would poison ecosystems. The oceans would darken as ultraviolet radiation penetrated their surface, wiping out plankton at the base of the food chain. It would be a mass extinction, not from impact or climate change, but from a silent flash of light from across the stars. This is not speculation without precedent. Geological evidence hints that something catastrophic struck Earth in the deep past, around 450 million years ago during the Ordovician period. A sudden die-off of marine life coincided with changes in atmospheric chemistry and climate. Some scientists suggest a gamma-ray burst as a possible trigger. Though the evidence is not conclusive, the idea remains plausible, and it underscores how vulnerable life can be to events far beyond its control. For astronomers, gamma-ray bursts are not only threats, but also opportunities. Their brightness makes them visible across cosmic distances, serving as lighthouses that reveal the structure of the universe. By studying their light, scientists can probe the earliest galaxies, measure the expansion of the cosmos, and learn about the formation of heavy elements. They are tools of knowledge born from destruction, showing us the universe in its rawest moments. There is a strange beauty in their dual nature. On one hand, they are weapons of extinction, capable of erasing life in an instant. On the other, they are signals that illuminate the history of the cosmos, offering insights into events that occurred billions of years ago. Each gamma-ray burst we observe is both a threat and a gift, a reminder of the violence of the universe and a source of knowledge about its past. The mechanics of these bursts remain an area of active research. The interaction between collapsing cores, accretion disks, magnetic fields, and relativistic jets is complex, and much remains uncertain. But what is clear is that gamma-ray bursts represent the extreme edge of stellar death, the most focused expression of the power of giant stars. They are the sharpened points of hypernovae, carrying destruction across light years with surgical precision. The question for us, living on a small planet orbiting an ordinary star, is whether such a burst could ever threaten Earth. The answer is sobering. Though the odds are low in any given moment, the possibility is real. Within our galaxy are massive stars capable of producing hypernovae and gamma-ray bursts. Most are too distant or too poorly aligned to endanger us, but the fact that it could happen at all is a reminder of our fragility. As we continue to explore the horrifying power of the universe's largest stars, the story of gamma-ray bursts leaves us with both awe and unease. They are proof that even in death, stars can reach across unimaginable distances to shape the fate of worlds. They remind us that the universe is not built with life in mind, and that survival depends on chance as much as on resilience. And yet, even these killers are not the final legacy of the giants. For when the explosions fade and the radiation beams pass, what remains at the heart of the collapse is something darker still. A black hole, a region where gravity is so strong that nothing, not even light, can escape. The birth of these monsters is the final act of the largest stars, and to understand their power is to look into the very limits of existence itself. The haunting truth about gamma-ray bursts is not only in their power, but in their reach. Unlike the localized devastation of a supernova, which reshapes only its immediate stellar neighborhood, a gamma-ray burst can sweep destruction across light years of space. A planet orbiting a distant star could be sterilized in an instant, with no warning, no chance of defense. Life might rise, flourish for millions of years, and then vanish in a heartbeat, erased by a beam of radiation from a star that died long ago and far away. The universe is vast, but its violence does not respect distance when channeled into such narrow streams of energy. And yet, paradoxically, gamma-ray bursts also illuminate the darkest reaches of the cosmos. Their brilliance makes them visible from billions of light years away, providing astronomers with rare tools to study the early universe. Light from some bursts has traveled nearly since the dawn of time, carrying with it information about the first stars and galaxies. By analyzing their afterglows, scientists can measure the chemical composition of galaxies, map their structure, and trace the expansion of the universe. These bursts are, at once, both weapons of annihilation and beacons of knowledge. The afterglows themselves are extraordinary phenomena. When the relativistic jets slam into surrounding gas, they produce shock waves that radiate across the spectrum, from X-rays to radio waves. These afterglows can linger for days or weeks, slowly fading as the energy disperses. They allow astronomers to pinpoint the locations of the bursts and to study the galaxies that host them. In many cases, bursts have been traced back to regions rich in massive stars, confirming their link to stellar collapse. In others, short bursts have been connected to the merging of neutron stars, proving that the universe has multiple pathways to unleash such violence. The implications for life beyond Earth are unsettling. In a galaxy filled with billions of stars, many of them massive enough to end in hypernovae, the odds are high that gamma-ray bursts have sterilized countless planets before life could evolve intelligence. Civilizations may have risen and fallen under their glare, erased from history before they could even reach their peak. This possibility suggests that life may be far rarer than we hope, not because it cannot begin, but because it cannot always survive. The cosmos is not only a cradle, but also a gauntlet, and gamma-ray bursts are one of its most merciless tests. Still, there is wonder in their existence. That the collapse of a single star can release so much energy, focused into beams that travel billions of light years, is a testament to the extremes of physics. They show us what happens when gravity, rotation, and magnetic fields combine in the final seconds of a star's life. They are laboratories of the extreme, natural particle accelerators that outstrip anything humanity could ever build. By studying them, we learn not only about the stars that produce them, but also about the fundamental laws of matter and energy. For Earth, the threat is small but real. No nearby star poses an imminent danger, but the galaxy is vast and the timescales are long. It is possible that in the distant future, a burst may sweep across our world. If it does, it will be swift and merciless, a reminder that life here depends on cosmic luck as much as on planetary stability. But whether or not it happens to us, it has certainly happened elsewhere. Across the galaxy, across the universe, worlds have been stripped bare by the unseen scythes of gamma radiation. And so, gamma-ray bursts remain among the most terrifying phenomena in the universe. They are the sharpest edge of stellar death, capable of annihilation across light years, yet they also enrich our understanding of the cosmos. They embody the paradox of the giants, destruction and creation intertwined, violence and knowledge born from the same act. But even these bursts are not the end of the story. After the beams fade and the afterglows diminish, what remains at the heart of the collapse is darker still. The giant's death often leaves behind a black hole, a region of space where gravity is absolute and escape is impossible. To move deeper into the horrifying power of the largest stars, we must now follow them into their final transformation, where light itself is trapped and where matter disappears into silence. When the greatest of stars meet their end, their final act is not always an explosion of light. Sometimes, their collapse is so complete, so overwhelming, that no brilliance escapes at all. Instead, they vanish into darkness, leaving behind an object so strange that it defies common sense. This is the black hole, the ultimate product of gravity, the silent heir of stellar giants. Where once a star blazed with millions of times the light of the sun, there remains only an invisible pit in space, a region where even light itself cannot escape. The birth of a black hole begins in the heart of a dying star. As fusion ceases and the core collapses, the pressure builds beyond all limits. If the collapsing core is heavy enough, greater than about 3 times the mass of the sun, no known force can halt the inward crush. Neutron degeneracy, the pressure that holds up neutron stars, breaks under the weight. Gravity wins absolutely. The core shrinks to a point of infinite density, a singularity, surrounded by an event horizon, the invisible boundary from which nothing can return. In a fraction of a second, the star's brilliance disappears, replaced by silence. To an outside observer, the collapse is eerie. The outer layers may explode outward in a supernova or hypernova, scattering matter across the galaxy. But the heart of the star is gone. If the collapse is direct, there may be no explosion at all. One moment, the star is shining. The next, it simply vanishes, leaving behind only its gravitational pull. A direct collapse is one of the most terrifying fates in the cosmos. There is no final blaze, no warning, only disappearance into the dark. Black holes born from stellar collapse are typically only a few times the mass of the sun, but the giants create larger ones. When a hypergiant like R136A1 collapses, the resulting black hole may be dozens of solar masses. These are heavyweights, lurking in the shadows of galaxies, invisible except through their effects. They warp space and time, bending light around them, pulling gas and stars into fatal spirals. They can devour matter with such ferocity that it heats to millions of degrees, shining in X-rays before vanishing forever beyond the event horizon. The concept of a singularity challenges our understanding of physics. It is a place where density becomes infinite, where the laws of space and time themselves break down. General relativity predicts their existence, but it also admits that it cannot describe what happens within. To peer inside a black hole is impossible, for no information escapes. They are not only physical objects, but also mysteries, barriers to our knowledge. Each black hole is a question the universe poses, one we cannot yet answer. The creation of black holes from stellar giants may also explain the seeds of the supermassive black holes found at the centers of galaxies. These cosmic behemoths, millions or billions of times the mass of the sun, may have begun as the remnants of massive stars in the early universe. Over time, they consumed matter, merged with other black holes, and grew into monsters that now shape the evolution of galaxies. In this way, the death of a single giant star may eventually influence the structure of an entire galaxy. And yet, for all their darkness, black holes are not empty. They are engines of energy, paradoxically among the brightest objects in the universe when feeding. Gas and dust falling into a black hole form an accretion disk that shines with ferocity, producing radiation across the spectrum. In some cases, these feeding black holes produce jets that extend for thousands of light years, sculpting the intergalactic medium. They are paradoxes, born of collapse, defined by darkness, yet capable of shaping the cosmos with streams of light and energy. The birth of a black hole is the final transformation of a giant star, the last step in a life that began with brilliance and ended in silence. To contemplate it is to confront both the limits of nature and the fragility of all things. Even the brightest, the most powerful stars cannot escape the pull of gravity forever. In the end, they vanish into the very force that sustained them, leaving behind shadows that will endure for as long as the universe itself. And yet, the story of black holes is not only about their silence. Their creation opens questions about the fate of matter, the nature of time, and the structure of the universe. To follow them further is to step beyond the deaths of stars into the frontiers of physics itself. But before we face those mysteries, we must return to a more immediate concern: whether the giants that create such horrors could ever threaten Earth. The question is not merely scientific, but existential. Could a nearby giant star endanger our world? And if so, how close is too close? The collapse of a giant star into a black hole is a process that unfolds in silence, but its consequences reverberate across the cosmos. When the core shrinks past the point of no return, the surrounding material responds violently. Gas and plasma spiral inward, colliding at extreme speeds, heating to millions of degrees, and emitting intense radiation before vanishing forever. This brief but furious accretion flare is sometimes the only sign that a black hole has been born. To distant telescopes, it appears as a sudden outburst of X-rays or gamma rays, a flash marking the star's disappearance into shadow. For black holes created from hypergiants, the violence can be even more extreme. If the collapse produces relativistic jets, streams of particles moving at nearly the speed of light, they can burst outward from the poles of the newborn black hole. These jets, tightly focused, may travel thousands of light years, shaping the structure of their environment long after the star itself has vanished. They are among the most dramatic displays of energy in the universe, paradoxically making black holes objects defined by their invisibility, some of the brightest beacons we can observe when they feed. The event horizon of a black hole, the invisible boundary surrounding the singularity, is both simple and profound. It marks the limit beyond which nothing can escape. Not matter, not light, not even information. To cross it is to be cut off from the rest of the universe, forever hidden. For an object the mass of 10 suns, the event horizon may span only a few dozen kilometers. Within that tiny space lies all the mass of a collapsed giant, compressed beyond imagination. It is an object so small in scale and so vast in density that the human mind cannot truly visualize it. To an observer watching from a distance, the collapse into a black hole appears surreal. As matter approaches the event horizon, time itself seems to slow. The falling star's final light stretches into longer and longer wavelengths, fading into darkness, as if the collapse never quite finishes. This is an illusion caused by relativity, a reminder that black holes are not only objects, but distortions of space-time itself. In truth, the collapse happens in moments, but the universe conspires to hide it from our eyes, leaving only the silent presence of gravity behind. The aftermath of such a birth is felt for eons. The black hole remains as a hidden anchor, pulling on nearby stars, bending their paths, and devouring matter that wanders too close. In binary systems, where a black hole orbits alongside another star, streams of gas may flow across the gulf, spiraling into the hole and lighting the system with deadly brilliance. These feeding black holes produce X-ray binaries, cosmic lighthouses that reveal the otherwise invisible presence of the collapsed star. Over cosmic time, some of these stellar black holes merge. Two black holes locked in orbit slowly spiral together, radiating gravitational waves as they lose energy. When they finally collide, the merger releases a ripple in space-time that travels across the universe. Detectors on Earth, like the Laser Interferometer Gravitational Wave Observatory, have already captured these faint tremors, listening to the final moments of black holes born long ago from stellar giants. Each detection is a story, the echo of a star's death recorded in the fabric of the cosmos itself. The birth of a black hole also represents a kind of permanence. While stars live and die, their remnants endure. Neutron stars may spin down, fade, and cool, But black holes do not age in the same way. They persist, growing if they consume matter, waiting in silence if they do not. Over billions of years, they can merge and accrete, becoming the seeds of the supermassive black holes that rule galactic centers. In this way, the death of one star may contribute to the shaping of entire galaxies, its legacy written not in light, but in the pull of gravity. And yet, black holes are not purely destructive. The energy released as matter falls toward them is one of the most efficient processes in the universe, converting mass into radiation far more effectively than fusion itself. They are paradoxical machines, born of collapse, defined by darkness, yet capable of lighting up the cosmos when they feed. The same giants that end in shadow create engines that illuminate galaxies, proving once again that in the universe, destruction and creation are inseparable. As we contemplate the births of black holes, we stand at the edge of knowledge. They are the ultimate consequence of gravity, objects where space and time themselves are bent to breaking, and yet they begin with something familiar: the death of a star. The largest giants give us the most terrifying reminders of what lies at the end of stellar life. But these monsters are not distant abstractions alone. The question remains: could such a collapse, such a death, ever threaten our own world? That question leads us back to our galactic neighborhood, where familiar names like Betelgeuse remind us that the universe's violence is never as far away as we might hope. The creation of a black hole marks the final surrender of a star to gravity, but its story does not end at the moment of collapse. What follows is a presence that endures across cosmic time, influencing its surroundings long after the light of the star is gone. These stellar black holes, forged in the deaths of giants, are scattered throughout galaxies like silent sentinels. Invisible on their own, they reveal themselves only through their effects, by the way they tug on nearby stars, by the X-rays they emit when feeding, and by the gravitational waves they send rippling through space when they merge. In a galaxy as vast as the Milky Way, astronomers estimate that millions of stellar black holes exist, the remnants of countless stars that lived fast and died young. Most are undetectable, drifting quietly through the dark, but some betray their presence in spectacular ways. When a black hole resides in a binary system with another star, its gravity pulls matter across the gulf, creating a stream of gas that swirls into an accretion disk. The disk heats to millions of degrees as it spirals inward, releasing energy that outshines the rest of the system. To distant observers, the star seems to flicker with strange brilliance, but in truth, it is the black hole feeding, its hunger lighting the void. The birth of these monsters also connects to one of the greatest mysteries of cosmology: the origins of supermassive black holes. Found at the centers of nearly all galaxies, these titans weigh millions or even billions of times the mass of the Sun. How such enormous objects formed remains uncertain. One possibility is that they grew from the black holes left behind by the universe's first generation of massive stars. Over billions of years, through accretion and mergers, they swelled into the engines that now shape galaxies. In this way, the death of the largest stars in the early universe may have written the blueprint for galactic evolution itself. The strange thing about black holes is that while they are defined by their invisibility, they are often associated with some of the brightest phenomena in the cosmos. Quasars, among the most luminous objects known, are powered by supermassive black holes feeding on torrents of matter. Relativistic jets, stretching across thousands of light years, erupt from the magnetic fields around spinning black holes. Even stellar black holes can produce bursts of radiation visible across vast distances. These paradoxes, darkness giving rise to light, collapse fueling creation, are what make black holes both terrifying and awe-inspiring. On a more personal scale, black holes remind us of the fragility of even the greatest stars. To think that Betelgeuse, Antares, or R136A1 may one day collapse into such objects is to accept that brilliance has limits. No matter how bright, no matter how vast, gravity is the ultimate victor. the end state of the largest stars is not eternal light, but eternal silence, a region of space forever cut off from the rest of the universe. The physics of black holes stretches our understanding. At the event horizon, time and space lose their familiar meanings. Near the singularity, the laws of general relativity break down, and quantum mechanics must step in, though we do not yet know how. To study black holes is to stand at the frontier of knowledge, where our theories falter and mysteries remain. They are not only cosmic objects, but also challenges, puzzles set by the universe itself. For all their terror, black holes are also reminders of continuity. Stars are born, they live, they die, but their remnants endure. The black holes of today are the echoes of stars that shone millions of years ago, their legacies preserved in gravity rather than light. Long after their explosions have faded, their influence continues, pulling, shaping, merging, and perhaps even helping to drive the growth of galaxies themselves. The giants die, but they leave behind monsters. Black holes are their final creations, their silent heirs, their shadows cast across eternity. To understand them is to understand that the universe does not waste. Even collapse and disappearance serve a role in the grand design, ensuring that the cycle of birth, life, death, and transformation continues. As we leave behind the black holes born of giants, we must ask a more immediate question. Could any of the great stars near us end their lives in ways that threaten Earth? To know the true stakes of the horrifying power of the biggest stars, we must look to our own galactic neighborhood, to the red supergiants whose fates we await, and to the possibility that their deaths may one day change our world. For all the grandeur of the stars we have explored, there lingers a question closer to home, one that transforms cosmic spectacle into personal concern. Could one of these giants, in its final moments, unleash destruction that reaches Earth? The universe is vast, and most of the hypergiants we have considered lie thousands or even millions of light years away. But scattered across our own galaxy, within distances small enough to matter, are several stars massive enough to end their lives in supernova or even hypernova. Their fates are sealed, their countdowns already ticking, and the consequences of their deaths depend not only on their distance from us, but also on the violence of their final acts. The most famous candidate is Betelgeuse, the red supergiant glowing at the shoulder of Orion. Barely 700 light-years from Earth, it is one of the closest and largest giant stars visible to the naked eye. Betelgeuse is already unstable, its outer layers swelling and pulsing, shedding matter into space in great arcs of gas and dust. Astronomers know that it is nearing the end of its life, destined to explode as a supernova within the next million years, perhaps far sooner. The idea that such a massive star, so near in cosmic terms, could end in such a blaze of violence invites both awe and unease. If Betelgeuse were to explode, the sight would be extraordinary. For weeks, its light would rival that of the full moon, casting shadows at night and remaining visible even in the daytime sky. It would outshine every other star, transforming familiar constellations. But for all its brilliance, the event would not threaten life on Earth. At 700 light-years away, the radiation would be diluted by distance. The explosion might disturb the heliosphere or slightly increase cosmic ray flux, but it would not strip the atmosphere or sterilize the planet. Betelgeuse, for all its grandeur, is close enough to awe us, but far enough to spare us. Other candidates lie scattered across the sky. Antares in Scorpius, another red supergiant, is larger than Betelgeuse, but much farther away, nearly 600 light-years. Its eventual death will be spectacular, but again, not dangerous for Earth. VY Canis Majoris, once thought to be the largest star by radius, lies nearly 4,000 light-years distant, far enough that its supernova will be only a point of brilliance to us. Even UY Scuti, the current record holder for radius, is so far from Earth that its collapse poses no risk. These stars are monsters, but they live in distant realms. The true danger would come not from ordinary supernovae, but from hypernovae, particularly those that produce gamma-ray bursts. These focused beams of radiation could devastate life across light years if aimed directly at a planet. Fortunately, the odds of Earth lying in the path of such a beam are small. The burst must not only occur within a few thousand light years, but also be oriented precisely toward us, a narrow target in the vastness of space. Still, the possibility remains, and the consequences would be catastrophic if it occurred. Astronomers have identified potential progenitors of such bursts within our galaxy. Wolf-Rayet stars, stripped down to hot, massive cores, are candidates for hypernovae. One example is WR104, a star about 8,000 light-years away in the constellation Sagittarius. Its pinwheel of dust, spiraling outward with its companion star, has drawn attention because of its potential alignment with Earth. If WR104 were to collapse into a hypernova and direct a gamma-ray burst our way, the results could be severe. At its distance, the burst would not vaporize Earth, but it could damage the atmosphere, disrupt ecosystems, and trigger mass extinctions. Scientists continue to study its orientation, but uncertainties remain. The idea that a star so distant could affect life here is unsettling. It reminds us that Earth, for all its stability, is part of a larger galactic environment, one shaped by forces we cannot control. The safety zones astronomers describe, distances within which a supernova or hypernova becomes dangerous, are narrow by cosmic standards. A typical supernova must be within 30 light-years to threaten Earth directly. A gamma-ray burst could reach across thousands. In the delicate balance of galactic survival, our planet's fortune lies in chance alignments and distances measured in light-years. And so the question remains, are we safe? The answer is yes, for now. No nearby giant star is poised to destroy Earth in the immediate future. Betelgeuse may explode tomorrow or in 100,000 years, but its brilliance will be a spectacle, not a catastrophe. Other giants are too distant. Hypernovae and gamma-ray bursts are rare, and the odds of one striking us directly are slim. Yet the possibility exists, and it reminds us that our survival depends not only on the Earth beneath our feet, but on the stars that light our skies. The possibility of a nearby stellar catastrophe lingers at the edge of our imagination because it forces us to confront our fragility on the cosmic stage. Earth orbits a stable, middle-aged star, one that will live for billions of years, but not all stars are so gentle. Across the galaxy, giants like Betelgeuse are ticking time bombs, their deaths inevitable, their power immense. We are fortunate that most lie at safe distances, but even then, distance is a thin shield when measured against the scale of these events. To understand the risks, astronomers define thresholds of safety. A typical supernova must occur within about 30 light-years to strip Earth's atmosphere or irradiate its surface with deadly cosmic rays. Within that radius, the ultraviolet and X-ray output from the blast would damage ozone, triggering cascading changes in atmospheric chemistry. For life, the consequences could be devastating. Mass extinctions would be likely, ecosystems collapsing under the weight of radiation and climate disruption. Beyond that radius, however, the danger diminishes rapidly. By the time the light of a supernova has crossed hundreds of light-years, it becomes spectacle rather than threat. Hypernovae and gamma-ray bursts, however, stretch this boundary outward. Because their energy is concentrated into narrow beams, they can affect worlds thousands of light-years away if aligned. The beams carry the concentrated fury of a collapsing core, their gamma rays able to strip away atmospheres and sterilize planets even at great distance. The chance of Earth being directly in the path of such a burst is small, but across the billions of years of planetary history, even small odds accumulate. It is plausible that life on Earth has already endured such an event, surviving only because the damage, though severe, was not total. The Ordovician extinction, more than 400 million years ago, is one candidate. Fossil evidence suggests a sudden die-off of marine species, coupled with a rapid shift in climate. Some scientists propose that a gamma-ray burst, striking Earth from thousands of light years away, could have destroyed much of the ozone layer, letting ultraviolet radiation pour in and devastate surface life. Whether this theory is true remains uncertain, but the possibility highlights how little control life has when faced with cosmic events. The fortunes of entire ecosystems can be rewritten by a flash of radiation from a dying star far beyond our galaxy's heart. Our position within the Milky Way offers both protection and exposure. We orbit in a region known as the Galactic Habitable Zone, far enough from the dense central bulge to avoid the frequent supernovae and hypernovae that occur there, but close enough to benefit from the chemical enrichment those explosions provide. Here, the risk of catastrophic events is lower, but not absent. We live in a galactic suburb where massive stars are rarer but not non-existent. Betelgeuse, Antares, and other red supergiants are reminders that even in quieter neighborhoods, giants can dwell nearby. The probability of a gamma-ray burst striking Earth directly in the near future is exceedingly small. Astronomers estimate that such events occur in our galaxy only a few times per million years, and the beams are so narrow that the odds of one pointing exactly at Earth are tiny. Still, on timescales of hundreds of millions of years, the odds are not negligible. Life on Earth has persisted for billions of years, but its history has been punctuated by sudden and dramatic extinctions. While impacts from asteroids and changes in climate explain some, cosmic events like bursts remain possible culprits for others. For humanity, the significance of this possibility is twofold. First, it underscores the need to understand our galactic environment. By studying the stars around us, by charting their fates and behaviors, we can assess risks not only for curiosity but for survival. Second, it reminds us that our existence is precarious, balanced on the quiet stability of our star, and shielded only by distance and chance from the violence of others. To look up at the night sky is to see beauty, but behind that beauty lies danger, hidden in the lives and deaths of giants. Yet even as we confront these risks, there is reassurance. Betelgeuse may explode within our lifetimes or in 100,000 years, but it is far enough that its death will be a show, not a disaster. Other giants are more distant still. Hypernova candidates like WR104 are thousands of light years away, and while their beams could be dangerous, the probability of perfect alignment with Earth is vanishingly small. We live in a universe where catastrophe is possible, but not inevitable, and so we watch. Telescopes scan the skies, monitoring the aging giants, measuring their pulses, searching for the signs of instability that signal approaching death. Each star tells its own story, and together they remind us that survival is never guaranteed. We are sheltered for now, but in the long arc of cosmic time, Earth is not immune. To live in a galaxy of giants is to live under the shadow of their deaths. The threat posed by giant stars is not just an abstract curiosity. It is tied to the very real question of whether our planet might someday face the consequences of a nearby stellar death. For now, the verdict is reassuring. No known giant star lies close enough to Earth to cause direct devastation. The safety margins defined by astronomers place us beyond the reach of ordinary supernovae, and while gamma-ray bursts are more dangerous, the odds of alignment are vanishingly small. But the fact that the possibility exists at all keeps scientists attentive, scanning the skies for the signs of instability that herald an approaching end. In practice, Earth lives within a cosmic balance. Stars like Betelgeuse and Antares are both close enough to awe us with their brilliance when they die, yet far enough to spare us their fury. Wolf-Rayet stars, potential hypernova candidates, are distant enough that even their beams of gamma radiation are unlikely to intersect with our planet. The risks, though real, are rare and low in probability. And yet, across the span of hundreds of millions of years, the improbable becomes possible. Life on Earth has endured extinctions before, some sudden and poorly explained. and cosmic events remain candidates for those ancient calamities. The perspective this brings is humbling. Our survival depends not only on Earth's own stability, but also on the galactic neighborhood in which we reside. We are sheltered in the outskirts of the Milky Way, far from the violent starburst regions where giants are born and die in greater numbers. This location grants us time and safety, a cosmic buffer that has allowed life to flourish here. But it is not a guarantee. The universe is dynamic, and the stars that live among us remind us that stability is always temporary. Still, the awe outweighs the fear. To witness a supernova in our sky would be to witness one of the greatest spectacles the cosmos has to offer, a once-in-civilization event. It would be a reminder not only of the destructive power of stars, but of the cycles that give rise to life itself. For without these explosions, there would be no heavy elements, no planets, no people to look up at the sky in wonder. Even the threats posed by giants are inseparable from the gifts they provide. As humanity looks to the future, our awareness of these risks shapes our curiosity. We build telescopes to study the aging giants, detectors to listen for the whispers of their collapses, and models to predict their behavior. We seek to understand not only for safety, but for meaning. The lives and deaths of the biggest stars tell us about the origins of the universe, the nature of matter, and the fragility of existence. They remind us that while we are small, we are also part of something vast, born of the same processes that one day will reshape the sky again. And so, the answer to whether a giant star could threaten Earth is both reassuring and sobering. Not today, not tomorrow, not in any future we can foresee with certainty, but over the immense sweep of cosmic time, the possibility lingers, as inevitable as the deaths of the stars themselves. The universe is not built with life in mind, yet life persists, watching the skies, aware of both the danger and the wonder written there. From this vantage point, we step into the final act of our journey. For while giants threaten with light and radiation, their true legacy lies in paradox. They are at once creators and destroyers, nurturing life through their ashes, even as they extinguish it in their deaths. The majesty and terror of stellar giants is the culmination of their story, a reminder that the horrifying power of the biggest stars is inseparable from the beauty of the cosmos itself. From the beginning, the giants of the cosmos have defied comprehension. They are born in clouds of gas and dust, gathering mass until their cores ignite with nuclear fire. They grow larger and brighter than anything our sun could ever dream of becoming, their light visible across vast gulfs of space. Some swell until their surfaces would engulf planets out to Jupiter's orbit. Others gather such immense weight that their radiation sculpts entire nebulae, dictating the birth and death of stars around them. They are the architects of galaxies and the destroyers of worlds, their lives brief but brilliant, their deaths catastrophic. To measure their size is to confront scales that stretch the imagination. Betelgeuse, a red supergiant nearing its end, would swallow Earth's orbit entirely if placed where the Sun now stands. Antares, the heart of Scorpius, is even larger, glowing as a swollen ember in the southern sky. VY Canis, Majoris, once thought to be the largest star known, extends more than 1 billion kilometers in radius, a bloated colossus shedding its outer layers into space. UY Scuti surpasses them still, a hypergiant whose sheer size defies any earthly comparison. And then there is R136A1, not the widest but the most massive, blazing with millions of times the luminosity of the sun, its radiation sculpting the tarantula nebula like a god of fire. Yet for all their grandeur, these stars are unstable. Their very size is their weakness, for the greater their mass, the faster they burn. The sun's quiet fusion will sustain it for 10 billion years, but the giants exhaust their fuel in only a few million. They race through the elements, from hydrogen to helium, from carbon to oxygen, until they reach iron, the dead end of fusion. At that moment, gravity wins, and collapse begins. What follows is destruction beyond anything humanity can truly imagine. Some giants end as supernovae, explosions so bright they outshine entire galaxies, scattering heavy elements into space. Others go further, becoming hypernovae, detonations 100 times more powerful, hurling beams of gamma radiation across light years. These gamma-ray bursts are the sharpest blades of stellar death, capable of stripping atmospheres from planets and sterilizing entire systems. Still others collapse directly into black holes, vanishing silently into darkness, their mass hidden behind event horizons that warp time itself. In every case, the result is transformation. The star dies, but in dying, it reshapes the cosmos. And this is the paradox at the heart of giants. They are terrifying, capable of annihilation on scales that dwarf human history, yet they are also the creators of everything we hold dear. The calcium in our bones, the iron in our blood, the oxygen we breathe, the gold we prize, all were born in the hearts of dying giants. Without their furious lives and catastrophic deaths, there would be no planets, no oceans, no life. Their destruction is inseparable from our creation. We are, in a very real sense, their children. To look upon these stars is to feel both awe and humility. They remind us that the universe is not gentle, that permanence is an illusion, and that even the mightiest blaze only briefly before fading. But they also remind us that beauty and terror are intertwined, that the same processes that threaten life also make it possible. They are titans, whose lives are measured in brilliance and whose deaths echo for billions of years, shaping galaxies and seeding worlds with the elements of existence. The horrifying power of the biggest stars is not only in their capacity to destroy, but in their role as the universe's greatest paradox. They are both monsters and makers, both executioners and benefactors. Their lives burn fast and end violently. Yet from their ashes come the building blocks of life and the architecture of galaxies. To understand them is to understand that creation and destruction are not opposites but partners, inseparable threads woven into the fabric of the cosmos. And so, we end where we began, staring into the vastness of the night sky, where these giants burn unseen distances away. Their fates are written, their deaths inevitable, their power unimaginable. They will collapse, they will explode, they will vanish into black holes, and in doing so, they will shape the universe itself. They are the titans of creation, the architects of destruction, the cosmic paradoxes that remind us what it means to exist in a universe vast beyond measure. The biggest stars are both creators and destroyers, cosmic giants whose horrifying power is the very force that makes the universe alive.